Welcome. Thank you for braving the morning traffic if you're a local person. A bunch of local persons will probably show up later due to the traffic. My name is Mark Carlson. I chair the SDC Agenda Committee, which has created and curated the content for you this week. I hope everybody's enjoying the conference. If you're not familiar with SNIA, we have a lot of things we're working on here. Persistent memory, we've got the whole hackathon going this week. In the Swordfish, we had a whole track on that on Monday. Physical storage, data management, data security, cloud storage, and storage management. So we work on standards, but we also have an interoperability lab and some conformance test programs that will make sure that everybody interoperates on a big standard. We also have various technology initiatives that may or may not make their way into standards. We have SNIA education, a whole library of content that you can go search on. We also do people certification where you can pass a test and get certified at a certain level of expertise. And then SNIA events like this one and others. So just a brief look at some of the things we've done in 2019 so far. We're planning to release the CDMI 2.0 by the end of the year. We also have a computational storage architecture and programming model that group is working on. LTFS version 2.5, it's on its way to ISO. There's a new work called the native NVMe over Fabrics drive specification. So if you want to get involved with that, contact the object drive twig. We have the NVM programming model. We're working on version 1.3 of that. Object drive key value API specification, we published that earlier this year. Persistent memory performance test spec. SNIA Emerald Power Efficiency Management Specification, SSM, or Swordfish Scalable Storage Management API, and the TLS version 1.1. And more, of course. The SFF twig is really prolific, and they come out with specs very quickly. And these are just a look at some of the ones that have already come out this year. So we have annual meeting call coming up in October. If you are the primary rep for your company to SNIA, you need to be on this call so we can get quorum and make some motions and so forth. We also have the annual members symposium. I believe that's right back here in the Hyatt, and that's in January. And then we have the Persistent Memory Summit that's always part of that. It's on January 23rd. Also on an international level, there's the SDC EMEA, February 5th in Tel Aviv, so put that on your calendar, as well as SDC India in Bangalore. Those are well-attended events with a lot of really good talks. A lot of them end up in our library as well. So thanks to our attendees and thanks to our sponsors, speakers, plugfesters. These are our sponsors. The size of the logo determines how much they paid. So we're going to have our general sessions in this room until lunch. We'll have lunch out in the sponsor showcase as usual. We'll have more breakout sessions this afternoon. And we have a networking reception and sponsor thank you from 5 to 7 p.m., just like we did last night, and then BOF meetings from 7 to 9. There is a mobile app. You can download the app, log in, and customize your agenda, download presentations while you're in the meeting, etc. Just get the link. From either a QR code or from typing it in, storagedeveloper.org. The interoperability lab is well underway, and these are the folks that are involved in that. This is a SMB3 interoperability lab. This is something that's been an essential part of our conference here for multiple years. And then Swordfish has a workshop going on. So SNIA wrote that. The Persistent Memory Hackathon was underwritten by the Solid State Storage Initiative. And these are our speakers this morning, and I'm going to introduce the first one right now. So Peter Onefrick is a fellow and NVMe Technical Workgroup Chair at Intel. He has been very active in NVMe standardization and is the current NVMe Technical Workgroup Chair. He holds over 40 patents, has written several published articles and books. Peter earned a PhD to electrical and computer engineering from Rutgers University and an MSEE from Purdue University. Please welcome Peter Onefrick.
Thank you, Mark.
Can you switch his?
Yep. So as Mark said, my name is Peter Onefrick from Intel, and I'm going to give an NVMe State of the Union, which is basically an overview of what is NVMe and what's happening in NVMe. So let's get started by taking a look at the historic NVMe organization structure. So we have a board of directors. The board of directors consists of 13 elected companies. You can see them on the bottom. The board is responsible for stewardship of the technology and basically setting the direction of the organization. Next, we have the technical work group. This is where the work where most of you that think of NVMe actually takes place. This is the work group that developed the NVMe base specification and where NVMe over Fabrics work occurs. Next, we have the management interface work group. The management interface work group standardizes management of NVMe storage devices. We'll go into a little bit about what that means a little later. Next, we have the marketing work group, which handles outbound communications, press releases, our website, and so forth. And then finally, we have the interop work group. The interop work group works with UNH IOL to help create our interop and compliance program. So that's an overview of the historic NVMe structure. A lot of you are here and you're thinking of NVMe as kind of this new or relatively new technology. And the fact is that NVMe has been around for quite a while. In fact, 2019 is actually the 10-year anniversary of NVMe. So on this 10-year anniversary, let's take a quick tour of the history of NVMe. So back in 2009, we had PCIe SSDs. There was Fusion IO. Micron had an SSD. The problem with PCIe SSDs in that time frame was that you had to load a special PCIe driver with each SSD. So you couldn't just plug in the SSD and have it work like you'd expect with storage. So we got together and decided that we needed an interface specification to basically provide that you just plug it in and it works behavior. So the idea was we were going to take NVMe HCI, which was an interface standard for client. We were going to add some enterprise extension to that, call that Enterprise NVMe HCI, and then basically that would be the new PCIe interface standard. We started work in mid-2009. The first specification came out in March of 2011. It was called Enterprise NVMe HCI 1.0, not NVMe 1.0. I put that there so I wouldn't confuse you guys. And Enterprise NVMe HCI came out, and we quickly, as soon as it came out, we realized we made a mistake. Enterprise NVMe HCI was not the kind of word that just kind of rolled off your tongue. The other mistake that we made is, we wanted an interface that was scalable from client to high-end enterprise. And the name Enterprise NVMe HCI really didn't encompass that. When you hear that, you think of just enterprise applications. So we changed the name to NVM Express, which is NVMe, which is what we all know it by today. Shortly after, actually weeks after we released the 1.0 specification, a competing standards organization decided that they were going to standardize a PCIe SSD interface. And interface war began. Proponents of that competing interface standard basically were claiming that NVMe was controlled by a single company, it wasn't opened. So to address those concerns, we transitioned the organization from an industry work group to a promoter structure. So basically the promoter structure is like a board of directors using the 13 elected companies and basically the same mechanisms that we have today. After that, in 2012, in order to kind of continue our interface war work, we realized that we needed a marketing work group to provide a consistent message external to the organization. So we created a marketing work group. We realized in order to be a effective industry standard, we needed to have a compliance program. So we partnered with UNH IOL to create compliance and conformance tests. We had our first PlugFest in 2013. At that point, we started seeing NVMe SSDs shipping, and we saw a number of OEMs deciding to standardize out-of-band management that they wanted for these SSDs. So we thought that the world would be a better place if we standardized out-of-band management, so we created the NVMe Management Interface Work Group to standardize out-of-band management. In 2014, we incorporated as a nonprofit, and by 2014, the interface war was over. NVMe had won at that point. We started seeing volume shipments of NVMe. And NVMe was kind of a great technology for inside the box. It used PCIe. Now, PCIe can scale to some extent, but it doesn't really scale like people would expect for a SAN. So work on NVMe over fabrics began in 2014. In 2015, we published the NVMe over fabrics spec. Later that year, we also released the NVMe MI spec. In 2017, our compliance program was going really great, but we wanted to get more involvement from the technical community to basically determine what features really needed to be tested in our compliance program and make sure that we got the appropriate industry input. So we created an interop work group. And then late last year, we ratified TCP as a transport for NVMe. So that's a brief history of NVMe. When you do an interface standard, one of three things, or when you do any kind of standard, one of three things can happen. The first thing is the standard can be stillborn. So you have a technical committee, they produce a spec, maybe some people make some prototypes, but it never really ships in any volume. So that's, I think we all know of specs where that's happened. Another thing that can happen is that the spec can get adopted, you can get some production shipments, but it only ships to kind of innovators and early adopters, and it never gets mainstream use. So it fails to cross the chasm into the mainstream, becomes a niche technology, and ultimately goes away. And then the third thing that can happen, which is the thing that we all want, is that it can become mainstream. And I'm happy to say that at this point, NVMe has crossed the chasm and become mainstream. So in the client world, high-performance SSDs and NVMe are largely synonymous. Market data shows that the NVMe and SATA crossover occurred last year. We continued to gain traction in the cloud, and we continued to gain share in the enterprise space. Looking at this data in a different way, we can look at the numbers. So in 2019, it's projected that we'll ship over 2 million enterprise drives, 17 million drives into the cloud, and over 100 million NVMe client drives. So I think NVMe has crossed the chasm and has become mainstream. I think the point at which I realized this was I was on vacation with my family in Washington, D.C. We're driving down the road, and there was a Supermicro billboard with NVMe all over it. And I realized that if I'm in Washington, D.C. and see NVMe on billboards, it's kind of become mainstream at that point. But NVMe is not only successful for PCIe SSDs, but it's now become the new language of storage. So we have 23 companies shipping 96 models of drives. We have 13 server companies shipping 93 models of servers. That's not surprising because NVMe SSDs are everywhere at this point. But NVMe is also gaining traction in a lot of other markets. So we have a number of companies shipping AFAs. We have a number of NVMe appliances. After NVMe over Fabrics was adopted, we had a huge number of companies supporting NVMe over Fabrics. We have 5 companies now shipping over 53 models of some form of NIC, RNIC, or HBA for NVMe over Fabrics. And we now have people building NVMe over Fabrics accelerators. You can think of these as kind of smart NIC companies. So with that brief overview of NVMe history and kind of the NVMe market, let's take a look at what NVMe has delivered this year. So this year, we released the NVMe Management Interface 1.1 specification in April. We released the NVMe 1.4 specification in June, and we're on track to deliver the NVMe over Fabrics 1.1 specification later this year. So where we're at is we've completed 45-day review. We've gotten some comments. None of them are technical. We need to integrate that and ratify it, but basically NVMe over Fabrics should be ratified shortly. So basically this year we have 3 new specifications. If you take a look at the organization, we've never had 3 specifications come out in the same year, so that's a real accomplishment for the organization. We've continued with our Plugfests. So we had Plugfest 11 in June of this year. And in that Plugfest, we have an integrators list for NVMe. We also have a separate integrators list and compliance program for the management interface, so we're testing that. We have tests for NVMe over Fabric, and we also have tests for NVMe over TCP. Taking a look at the NVMe specification roadmap, we have 3 swim lanes, which represent the 3 specifications that we produce. At the top, we have the NVMe base specification. So this is the specification that defines the NVMe architecture, the NVMe command set, and the transport binding specification for PCIe. Below that, we have NVMe over Fabrics, which basically describes how do you scale the NVMe command set and the NVMe architecture over arbitrary fabrics. And below that, we have the NVMe management interface specification. So historically, the management interface specification defined how do you do out-of-band management. Now it encompasses more than that, and we'll see some of that a little bit later. So in 2019, we have the 3 specs that I showed you. You can see beyond that, we have NVMe 2.0. And NVMe 2.0 is going to be a major refactoring of our specifications, which I'll describe a little later. But before we get into NVMe 2.0, let's take a look at some of the details around the NVMe specifications. So in NVMe 1.4, we have 3 big new things. The first is NVM sets and I/O determinism, which basically describes a way to get better QoS from NVMe storage devices. I'll go into what this actually looks like a little bit later. We have the persistent event log. You can think of the persistent event log as kind of a black box flight recorder for NVMe storage devices. Basically, you can record events in the persistent event log. Then if there's a failure, either an OEM or the original drive manufacturer can basically look at the persistent event log and see what happened. Now, a lot of you are probably thinking, well, this is really nothing new. We've had persistent event logs in SSDs forever. I think what's new here is that this is now standardized. So anybody can dump a standard log page. They can parse the persistent event log and see what's going on. Now, it's no longer vendor specific. And the third big thing in NVMe 1.4 is multipathing. Now, we've had multipathing in NVMe since NVMe 1.1. We added, multi-ported drives and multipathing. But what we've added is basically the ability to figure out how to select the best path, and I'll describe that a little bit later. For NVMe over Fabrics, we have 2 big new items. The first is an enhanced discovery system. So in NVMe 1.0, we had discovery, but it really wasn't scalable. We wanted a system that was more scalable to kind of thousands of nodes. So we've made those enhancements in an enhanced discovery mechanism. The other big new thing in NVMe over Fabrics 1.1 is the TCP transport binding specification. So this basically allows you to run NVMe over TCP, and I'll describe that a little bit later. NVMe MI has 3 new things as well. The first is enclosure management. I'll talk about that a little bit later. The second is the in-band mechanism. So recall NVMe MI initially specified out-of-band management. And what we found is a lot of things that we want to do out-of-band, we also want to be able to do in-band. We want to be able to download firmware. We want to be able to format namespaces. Those mechanisms existed through admin commands that are executed in-band. So rather than defining new out-of-band commands, we've had a way to basically issue those admin commands using the out-of-band mechanism. And then we built up additional capabilities in NVMe MI. And what people wanted is they want basically symmetry. They want to be able to get the same management capabilities in-band that they have out-of-band. So what the in-band mechanism does is it allows you to execute NVMe MI or issue NVMe MI commands in-band. And this is particularly useful for enclosure management. Finally, we made extensions to what an NVMe storage device is. I'll describe what that is and what the extensions are a little bit later. So let's turn our attention to I/O determinism. I/O determinism has 2 parts, NVM sets and predictable latency mode. So what an NVM set is it's basically a logical partition of the NVM associated with an NVMe storage device. And these are QoS isolated partitions. So an NVM subsystem may have one or more NVM sets. You can put one or more namespaces on an NVM set, and they're completely isolated from a QoS perspective. So in this picture, we have, you can think of this as an NVMe storage device. We have 3 NVM sets, A, B, and C. A has 3 namespaces, B has 2 namespaces, and C has 1. And basically, these are all on the same drive. And what NVM sets allow you to do is read or write to NVM set A without impacting the QoS associated with NVM set B. So that's the fundamental idea of NVM sets. The next thing that we added, or the next piece of I/O determinism, is predictable latency mode. So we can take an NVM set and we can turn on predictable latency mode for an NVM set. And what that does is it causes that set to basically oscillate between 2 states, the deterministic window and the non-deterministic window. The deterministic window is basically a state where you get great QoS. The non-deterministic window is a state where basically you do all your background operations and you actually execute any writes that were issued during the deterministic window. So basically, you can do reads during the deterministic window, and you get very good QoS. You can do some number of writes that get buffered, and then you transition to the non-deterministic window. Those are executed, and then you oscillate back and forth. So basically, you go between the deterministic window and the non-deterministic window. So this by itself isn't really that interesting, because when you need to do a read, you need to do a read. And the fact that you've got this deterministic window doesn't really help you. But what you can do in some environments, and this is primarily targeted towards cloud environments, is that you can take 2 SSDs, you can take a set on each, and you can put them both in predictable latency mode. So now they're oscillating between the deterministic window and the non-deterministic window. And you set them so they're out of phase. When you do writes, you write to both SSDs. When you do reads, you target that read at the SSD that's in the deterministic window. So now you have a way of getting great QoS. So I showed this example with 2 SSDs, but you can actually do it with 1 SSD because you can put multiple sets on it. So it works with sets on a single SSD. So as I mentioned earlier, NVMe is gaining adoption in a variety of different use cases. One of them is high-end storage systems. So here's a picture of a high-end storage system. Think of this as refrigerator-sized boxes that fill a room that are interconnected. As you'd expect, NVMe SSDs are a key part of those storage systems. But NVMe is also being used in the front end. So here we have an NVMe storage system, which is one of these room-filled arrays. We have multiple hosts. They connect to this storage array through NVMe over fabrics. And what these hosts see are basically a single NVM subsystem. So in these sort of applications, you get some unique issues. So this picture shows a logical representation of the NVM subsystem associated with a storage array, or potentially with a storage array. Here we have 3 controllers. There's a host port associated with each controller. We have 4 namespaces, A, B, C, D. Namespace A is private. B, D, and C are shared namespaces. And basically, we have a media access boundary. So think of this as we have 2 refrigerators. They're interconnected, and the interconnection between those 2 refrigerators is the media access boundary. Now, what may happen in that and they all act as one NVM subsystem. You can have a host that has multiple ports into that NVM subsystem. So a host, for example, can use port X or port Z to access namespaces in that NVM subsystem. So let's say we're trying to get to namespace B. It may be the case that access through port X to namespace B may be higher performance than coming in through port Z because it's got to go through this media access boundary. So what asymmetric namespace access does, or ANA, is it's basically a mechanism to allow the NVM subsystem to communicate to the host, here are the different paths, and here are the good paths to use to access the NVMe, the namespaces. So it will tell you that port Z is the better path to use than the port Z. So it's kind of a multi-pathing enhancement. The other thing that can happen in these refrigerator-sized arrays that are interconnected is that this media access boundary may break. So it may be the case that you can't access namespace B through port Z. And ANA basically provides a way for the NVM subsystem to communicate that to the host as well. So that's NVMe. Let's turn our attention to NVMe over fabrics. This slide shows a taxonomy of NVMe transports. So on the left, we have the memory transport, which is used by PCI Express. And then we have the message and memory transports, which are used by NVMe over fabrics. So the message transport really uses a thing called capsules to transfer commands and completions, and it uses messages. An example of the only example up until NVMe over fabrics 1.1 of a message transport was fiber channel. The message and memory transport uses capsules for commands and completions, but uses memory semantics for transferring data. Examples of that are the RDMA transport, which works over InfiniBand, RoCE, iWarp, and so forth. So what's new in NVMe over fabrics 1.1 is TCP. So the advantage of TCP versus these other transports is that you can basically run NVMe over TCP over any fabric that supports TCP. That means that you can use normal NICs. You don't need to buy special NICs. You can use normal switches. You don't need to buy any switches. So you might be thinking, well, that's interesting. I mean, we've run other storage protocols over TCP. That's nothing new. But actually, TCP is actually very interesting. So this slide shows performance of the NVMe over TCP implementation, the open source implementation, versus NVMe over RDMA using InfiniBand. Now, as with all performance data, your mileage may vary, but basically what this data shows is the red bar is the latency adder that InfiniBand adds, and the blue bar is the latency adder that TCP adds, and that's on top of what you would get to a direct attached SSD. So what you can see is TCP is about double that of InfiniBand or RDMA. RDMA adds about 10 microseconds. TCP adds about 20 microseconds. So it's double. That seems really bad. But when you put this into context, you think of, OK, a normal NVMe SSD has a read latency of, let's say, 80 microseconds. RDMA is adding 10. So you're basically comparing 10 microseconds for 90 microseconds for RDMA versus 100 microseconds for TCP. And so TCP allows you to disaggregate that storage without buying any special hardware, and the latency is actually quite good, and throughput's quite good as well. So as with any performance data, your mileage may vary, but it is an interesting technology. Moving on to NVMe MI. With the success of NVMe SSDs, people want to build NVMe JBOFs. So an NVMe JBOF is just basically a JBOD with flash that uses NVMe SSDs. A logical, or basically an architectural block diagram of what that is shown on the left. So we have an NVMe host, which connects to a PCIe switch, which connects to a bunch of NVMe SSDs. And then we have an instantiation of that on the right, which is basically the Facebook Lightning platform, which has an implementation very much like the one on the left. So one of the areas that you get into with enclosures is enclosure management. And the MI workgroup has standardized two forms of enclosure management. I worked at a company that builds SAS expanders, and my SAS expander buddies kept telling me that NVMe or PCIe would never succeed because it doesn't have enclosure management. And I always found that strange because I'd been shipping PCIe switches since day one, and we never provided any management software. For normal fan-out switches, I couldn't really figure out what the gap was. And what it turned out to be is basically indicators. So for very simple in-box expander applications, there's a need for indicators. The MI workgroup defined an extension to PCIe to do this. We brought that into the PCI SIG, and it was standardized. It's been around for a while now, and it's called Native PCIe Enclosure Management. It just allows you to control indicators with drive slots. And it's called MPEM. So that's fine for very basic enclosure management, but sometimes you really need real enclosure management. And that's what we've added to NVMe MI 1.1. If you take a look at NVMe and SCSI, the architectures are actually very different. But if you take a look at SCSI enclosure services, what an enclosure is for SCSI is very similar to what an enclosure is for NVMe. They contain a bunch of sheet metal. There's some power supplies, fans, temperature sensors, and so on, and you basically want to manage that. If you take a look inside of SES, you find out that there's actually very little SES or SCSI-specific stuff inside of SES. So what we've done in the management interface group work group is we've leveraged SES. We've provided a tunnel from NVMe MI to SES, allowing you to use SES for enclosure management to build NVMe JBODs. So that's enclosure management. A second addition to another big addition to NVMe MI 1.1 is an extension of NVMe storage devices. Now, in NVMe, we have this concept of an NVM subsystem. That's kind of a logical thing that we talk about in the NVMe base specification. But when you're providing management, you need to actually manage something, which is a physical thing. So we needed a definition for the physical thing that we were managing. And so we're managing NVMe storage devices. So an NVMe storage device is one NVM subsystem, one or more ports, and an optional through information device and an SM bus interface to get to that through information device. So there's two examples on this slide. So example on the left is just a straight PCIe add-in card with single ported, one NVM subsystem. On the right, we have a dual ported drive, so dual PCIe ports. We have a VPD and out-of-band SM bus management interface. And this model served us well for a number of years. But basically, people are now building much more complex NVMe storage devices. So what we have is the device on the left, which is basically a carrier card. It has a PCIe switch. You can plug in two NVMe SSDs into it. We can't manage that because we can only handle one NVM subsystem. We don't understand what happens when there's a PCIe switch on an NVMe storage device. Another example that's common is on the right, which is a carrier card. Here we have a by16 card that bifurcates into 4x4s. It's got 4 M.2s. Again, we can't manage this because we don't understand what a carrier card is and how to deal with it. So what we've done in NVMe MI 1.1 is we've extended the definition and extended our management model. We can now manage multiple NVM subsystems. We can discover and manage PCIe switches. We can discover the SM bus topology and control muxes to talk to those NVM subsystems. And we understand connectors, and it can express the topology of the connectors. So we've adapted and can now handle much more complex NVMe storage devices. So that was an overview of kind of what's new in the specifications that were released this year. Now let's take a look at kind of the NVMe organization in general. And the NVMe organization has undergone, has going through 3 phases. In the first phase, it was all about a PCIe SSD interface, right? We wanted to have the same look and feel as what you have with a drive. You just plug it in and it works. So it was all about standardizing the PCIe interface, getting NVMe drivers written, getting them in box in all the major OSs. I'm happy to say that phase 1 is done at this point. PCIe and NVMe is largely synonymous, and there's an NVMe inbox driver in pretty much every major OS at this point. In phase 2, NVMe SSDs got adopted in box. We wanted to scale outside the box. So it's basically all about NVMe over fabrics. And while work continues on NVMe over fabrics, we're largely done with that. The underpinnings of NVMe over fabrics are done. You can deploy NVMe over fabrics. We will continue extending it forever, like we will with PCIe. But that work is largely behind us as well. So we're now entering the third phase of NVMe, which kind of has 2 pillars to it. The first pillar is around standardizing mechanisms that are specific to NVM. So this is now using the unique properties of NVM and providing standard interfaces to that. So the I/O determinism mechanisms that I talked about earlier, that relies on NAND, are specifically targeted for NVM. Zone namespaces are another mechanism that are specifically targeted towards the unique properties of NAND. So that's the first pillar. The second pillar is entirely new use cases for NVMe. So as I mentioned, NVMe is gaining adoption in large storage arrays. That's been happening for a number of years. But NVMe is now getting interest from entirely new markets, such as automotive, which have very new requirements for NVMe. So we're now in the third phase of NVMe. The unique thing about the third phase of NVMe is that a lot of these initiatives are highly speculative. So if you remember, one of 3 things can happen to a standard, and only crossing the chasm in mainstream adoption is the good outcome. So it's clear that some of these initiatives may not succeed, may be stillborn, may become very niche. We need a way to manage this complexity. We don't want this specification to grow out of control and become hugely complex. So the way we're managing this complexity is we're repartitioning or refactoring the specification. So at the center, there'll be an NVM NVMe base specification, which will describe the base architecture of NVMe used in all applications. Above that, we'll have command sets. So today, you're probably only aware of the NVM command set, but we're working on a key value command set and a zoned command set. We will probably continue to add application-specific command sets. So that's at the top. At the bottom, we're going to pull out the transport binding specifications into separate documents. So there'll be one for PCIe and so forth. So now we'll have a family of specifications. And if you're building a solution for targeting a particular market, you can basically pull out the specifications you need and ignore the other ones. And if we come up with a command set or a transport that doesn't gain traction, it will just fade away and nobody will see it because it'll be segmented in its own document. So one of the net results of this is we're going to take the 3 monolithic specs that we have and now refactor them into a pool of specs. So that's a spec restructuring, but that restructuring has also caused a restructuring of the organization. So this is the new structure of the NVMe organization. What I showed you earlier was the historic structure. So the new structure is we have a board of directors. The board of directors, still 13 companies. It is a steward of the technology, sets direction. Now we have 2 work groups. We have a marketing work group where we handle outbound marketing, and we have a technical work group. The technical work group will continue to be the place where the core NVMe technical work is done, but it'll also act as a plenary session to basically coordinate all the other work that's going on. And then we're moving to a task group structure. So a task group you can think of as a work group in the sense that a task group has a chair. It has a publicly published meeting time that's available on the NVMe calendar. The chair is responsible for sending out an agenda before the meeting. The chair is responsible for sending out meeting minutes. So it operates very much like a work group, but it's basically below below a work group. And we have 2 types of task groups. We have a topic task group, and we have a single technical proposal topic task group. Topic task group is basically intended for kind of long-running things. So things like the management interface, interop, ANA. We think that these things will continue pretty much indefinitely. We'll be adding new things or issues will be coming up and there'll be errata discussed. So we need a place for that to occur. So that's topic task group. The other type of task group is a single technical proposal task group. So basically here we'll spin up a task group. It'll work on a single technical proposal. When the technical proposal is done, that task group goes away. Now, it may be the case that some of the topic-specific task groups some of the technical proposal task groups turn into topic task groups, if they're widely adopted, but that basically, we'll see how that happens. So topic task groups are things like the key value command set, endurance group management, spec refactoring, zone namespaces. Topic task groups are management interface, interop, and ANA. Now, you guys may be looking at this and going, well, the management interface and interop previously were their own work group. Now they're a task group. Does that mean we're not we're removing emphasis on management interface, for example? And that's completely not the message that we're trying to send. What we're trying to say is we have a lot of technical activities going on in NVMe now. We have a lot of specs moving in parallel. We need a way to keep them all in sync, and the technical work group is the place that will keep them all in sync. And basically, this just basically allows us to parallelize the work. So NVMe has grown over the years. We started off as kind of a scrappy little organization defining a PCIe interface, and now it's the new language of storage. Much in the same way that companies transform as they go from a startup to a mid-sized company to a Fortune 500 company. You can't run a Fortune 500 company the way you run a 50-person startup. You can't run an organization like NVMe today like you did when we first started. So we've made a number of changes. First is we've moved to the task group structure, which will allow us to improve the throughput and keep everyone in sync. The second thing that we've done is we've created formal technical proposal phases. So basically, each technical proposal now goes through phases. We know what's done in each phase. We can track the phases. We have a document repository where you can look at, it's in the members only area. You can see where each TP is, what the status is. You can go through the revision of that TP. We've instituted a policy of creating an integrated draft specification prior to releasing any TP. What we found in NVMe 1.3, we had about 20 technical proposals. They all looked great on their own. We then wanted to release the spec. We tried to integrate them, and we found out that some codes were reused and some text didn't quite agree. So now what we do is before a technical proposal is ratified, we integrate it into the running draft spec, and we handle any of those sort of issues prior to ratification of the technical proposal. Finally, we were first started out, we had in-group voting, allowed us to move very quickly, be very nimble. But now we deal with a lot of companies that are multinational, they have many sites, and we now move to electronic voting, which allows people to coordinate their votes prior to doing that. So in summary, NVMe has unified client, cloud, and enterprise storage around the common command set and interface. It truly is the new language of storage. The growth of NVMe adoption continues. You can see by the numbers, we've crossed the chasm. It's mainstream, and the growth continues to keep going. The NVMe organization has put in place a number of processes and initiatives to continue the rate of innovation, basically embrace all of the people that are trying to enhance NVMe, but do that in a way that compartmentalizes complexity and doesn't cause everything to be very complex if you're trying to build a very simple device. Finally, as NVMe enters its second decade, it remains true to its core principles of simplicity and efficiency. Thank you.
With the mic. Hi, so my question is with the sideband access, NVMe MI, this is a SNIA consortium, so we heard about Redfish and we heard about Swordfish, and to me, as a consumer of storage, it sounds like yet another protocol. Is there a coalescing of them?
Yeah, so NVMe MI existed because basically nothing like that existed when we started work on that. It's largely deployed in PCIe SSDs. We know of Redfish and Swordfish. In fact, Mark has an outstanding TPAR to try to coordinate those activities. So we're aware of it and trying to address that. Any other questions? Okay, thank you.
Okay, so our next speaker will be Gilbert Bouzade, is that right? Yeah, he's the lead product manager for eBay storage, including block and object storage. He has more than 2 decades of experience as technical product management and software architecture, and specializes in large distributed workloads running in the cloud. He's a frequent speaker on the topic at conferences around the world, and we're glad to have him here today. We are running a little bit early. No? Is he here, Marty? I don't know. Can you check? Well, while we're on the break, I'd like to ask Tom Coughlin to come up, but he's not here either. Yeah. He just left. Go meet him out in the hall, quick. still out there. Okay, shortly. Okay, please welcome Gilbert from eBay.
Hello, everyone. My name is Gilbert. I'm the lead product manager for eBay Data Storage Solutions. I'm here today. I'm going to discuss about object storage at scale at eBay. And so I'm going to go a little bit over the history of object storage at eBay, where we're using object storage, small comparison with other storage, and then drill down into kind of one of the object storage solution that we leverage, and how we were able basically to scale it for our workload and for our business requirements. Okay, before discussing technicalities, just a glimpse of eBay, the company. So we have StubHub, we have eBay Classified Group, and we also have eBay Marketplace under the eBay Inc. umbrella. Our GMV is about 22.6 billion. And we have about 14,000 employees, 182 million active buyers, and 61% of international revenue. In terms of cloud infrastructure, this will give you an idea about kind of, the eBay cloud we're dealing with. We have about 300,000 managed VMs. Also, we have 80,000 managed bare metal, and over 100 petabyte of managed storage. Here, I'm not referring to storage, local storage or anything, that the user can spawn on their compute box. I'm referring basically mainly to managed storage, including block storage, including object storage, etc., etc. Also, we have about 150,000 containers, as well as 5,500 managed application. And we receive around, in the infrastructure, we receive around 400 billion requests a day. Here I'm listing some of the eBay cloud strategies. Pretty much, the full cloud team is focusing on. The first one is kind of, we're fully embracing Kubernetes, getting away from compute to OpenStack. We also have a huge initiative related to designing and leveraging our own servers. And this is basically helping us in terms of optimizations. So we're optimizing the hardware based on the workloads, the specific workloads that we have at eBay, but also it's helping us in terms of cost as well. The third item is related to building our own AI engine. And this is something, I mean, the AI engine has already accelerated the production of new features such as computer vision, image search, and social sharing. We are fully focusing on building point of presence, and this is targeted towards helping our end users or in order to get faster downloads when using eBay. So by implementing kind of more and more point of presence, we were able to save about 600 to 800 milliseconds of load time for our end users. And the last one part of the big strategy is related to open source transformation. And talking about open source transformation, we're using many open source products, and we're contributing to those products as well, including Envoy, including MongoDB, Docker, Apache Kafka, and Swift. And here Swift, I'm referring to the Swift object storage, definitely not the programming language. So this is perfect segue, since I'm going to talk now more deeper about kind of the object storage. And so I'll start these slides around there. First, I mean, what is object storage? Object storage, think of it as basically you have the data storage architecture that manages data as objects, as opposed to storage architecture that manages data as blocks or file system. Why object storage is very important? Because one of the main reasons is object storage can scale very high. So definitely, I mean, when we're discussing about high numbers in petabyte or even exabytes, object storage basically is always highlighted as a great solution for those type of use cases. How the object storage need was identified at eBay. So definitely, as many of you know about the eBay marketplace, the eBay related business, there's a huge data that is needed to be stored, including, I mean, images, including, I mean, content related to buyers, content related to sellers, but also everything, I mean, kind of from the back-end system, I mean, related to logs, et cetera, even kind of data that has to be archived, and so on and so forth. So with the need identified, we start looking into various object storage solutions. And talking a little bit about the history around object storage at eBay, the first solution, we call it EPS, which is eBay Picture Service. This one was released in 2007. And this one basically was the solution where, I mean, it stored all images for eBay. So I mean, when you were kind of going to eBay website and kind of the images were being fetched or from this service. In 2008, we introduced EMC Atmos. 2012, we had our own in-house object storage solution called zStore. zStore replaced fully EPS, and zStore hosts all images currently of eBay. And then 2014, we started introducing Swift object storage. And Swift object storage, basically throughout 2017, we were able to replace fully EMC Atmos. And currently, I mean, Swift object storage solution is growing within eBay. And part of my talk, I'm going to discuss mainly kind of about this solution and how we took it further within the company. Why Swift? Why not other? I mean, there are so many object storage solutions available on the market. Swift was chosen in 2014 for several reasons. One of the some of the reasons I listed them here. The first one is related to high scalability and reliability. The second is about, it's a pure software-based solution with providing a REST API. The REST API is Swift API, but also, you can have the S3 API as well. On top of it, Swift is highly elastic. Also, you can provide replication or erasure coding. You can provide multiple policies, based on the account, a container, et cetera, et cetera. And then also, Swift is a stateless service. One last important thing I would like to mention is Swift run on heterogeneous hardware. And this is really kind of helping us as we're going into building our own servers. We have kind of specific hardware and kind of, sometimes it can be a mixture. And we're able to accommodate and leverage those hardware with Swift very easily. Okay, talking a little bit about the deployment diagram. Here I'm referring actually, to a case where there are 3 replica. So a theoretical case where basically there are 3 replica, we're replicating them across multiple data centers. In terms of flow, the end user will be requesting, providing the token, will be requesting from the GTM the Swift endpoint. And the GTM will reply to the end user with the endpoint that is closest to the location of this end user. So in this case, this location, let's say, is data center A, and the end user will be able to, to upload or download a file, from location A. Here I'm mentioning, this is basically the high-level architecture or deployment diagram, for basically a replication use case. You may ask me, oh, well, if the user is uploading actually a file from or to data center A, how it's going to be in terms of how the replica will be made. So one thing you may want to note is this data center will be responsible of replicating the data on the 2 other data center. And the way Swift work, or the way you can set it basically is you don't reply back to the end user unless at least basically a quorum has been formed, or more in this case, basically, let's say you have a replica of 3, you can mention that, okay, at least I have basically 2 objects that were saved, or 2 replicas that were saved, and then I return back to the end user. Giving you some statistic into our current Swift object storage solution. So we currently handle about 2 billion objects. We have 2 million containers, 900 accounts, and we receive about 25,000 requests a day. Second, sorry. We have around 5 petabyte of storage currently on Swift. And in terms of bandwidth, is around 30 gigabyte per second. In terms of our customers, who are mainly the Swift object storage customer? Again, what I'm discussing about is a fully internal solution. So our customer are domain teams internal to eBay. But those domain team, provide basically tools or web application or mobile application that are end user facing or public internet facing. So they're using Swift in order basically to have their data stored on it. So some of our customers include Seller Hub. Some of you may be familiar with the feature on eBay. Other customer related, to the deployment. So we use basically Swift part of the deployment process. The third one is related to return shipping label. Fourth is about transaction logging. As I discussed earlier, there is a huge amount of logs, within eBay. So this object storage solution, is used somewhat, for those use cases. We use it also for image search. We use it on PCI, PII related zone or compliance. We use it for Elasticsearch index backup and also the last one related to zone transfer. About zone transfer, I'll explain a little bit further what I mean by that. And so I'll give a little bit a brief about how our Swift cluster is connected. It's multi-tenant and multi-zone, and I'll give some background around this. Okay, one thing I mentioned about our Kubernetes initiative earlier, and part of this initiative and part of having or providing object storage, we ensured that Swift object storage solution is working very, very closely with our Kubernetes drive. So, one of the first item we had on the list is we had the eBay container registry, backed by Swift. The other item or part of Kubernetes and Swift object storage is related to we ensure that our customer are able to leverage fully the Swift cluster from Kubernetes solutions, and that their account is created offline seamlessly. Also, we provide for some user who would like to try out basically Swift object storage in their environment. We provide a Swift running on Kubernetes that they can customize for their own need. Here I'm going to be talking about some of the challenges and solutions that we provided. Again, so Swift is an open source product. We use it and then we enhance it to our workload. And part of enhancing it, we ensured that we resolve any challenges that are specifically to eBay. The first challenge we encountered and we resolved. A few items I listed here just to summarize or to give some highlight about this challenge. So we're providing what we call a global Swift solution. And think of it as one cluster that is used for all workloads, for multi-tenant and multiple zones. And this cluster is handling a huge number of use cases, of course. We encounter on this cluster definitely a very large number of concurrent access. And also, when we deployed this cluster, we used a firewall, we used a load balancer, and we find out basically our limitation was not Swift object storage itself, because Swift actually can scale, so it can horizontally scale, so, to clarify. But some of the main bottleneck that we had is related to the LB and firewall that are fronting this solution. So, what did we do in order basically to encounter or to resolve some of the problems? One of the first things is we started a program about educating our customer. How they should be using Swift. Many of our customer, or when we started discussing with our customer, they had some notions about object storage, But in order for them to leverage it, I mean, to the maximum, I mean, we had to educate them further and give them some best practices and what they should do, what they should not do, et cetera, et cetera. So we find out basically having educational sessions, I mean, for our customer really, really helped in terms of usage, in terms of basically kind of optimizing object storage for their use cases. Also, I mean, one thing we kind of worked out kind of on our Swift backend is we split the Swift services. And what I mean by that, I'm not sure if some of you are familiar with Swift, but Swift, there are 4 main components. One is we call proxy. The other is account, then you have container, then you have the object. Object is basically kind of the stored data, right? Account container is, I mean, related to the account. Container is similar to a bucket in AWS. And then proxy, think of it as basically, I mean, exactly, I mean, like a proxy. It's just basically receiving a request and directing it, I mean, to the right account or getting the right account container and directing it to the right object. So what we did, we separated the proxy or kind of, I mean, the proxy account container. We had them on one box. And then we had the object on another type of box. And the box that we used, or kind of the node type that we used for the pack, we call it the pack node for proxy account container. It's a high performance type of node. So high on CPU, memory, and having SSDs. And the object node is basically very high on disk storage, but using hard drives or spindles. So think of this node basically in terms of cost is very, very cheap. You know, I mean, in terms of cost per terabyte, right? I mean, this is very cheap. I mean, this is more expensive, but we have only few of the pack nodes. And with this solution, we were able to optimize and to save on cost. So definitely, this turned out to be very good solution, I mean, for our use cases. And the last item, basically, that we did, as I was mentioning before, I mean, load balancer was one of our bottlenecks. So what we did, instead of just kind of getting more hardware load balancers, and it's very expensive, we got into a mode where we're getting basically more software load balancer, and we're able to scale them very easily and kind of on demand sometimes. So this worked out pretty well. The second challenge that we face, and some of you also may face as well. I mean, again, I mean, this is an internal solution. So usually there's no kind of dollar amount that are really kind of shared. I mean, there's dollar amount at the high level. I mean, within kind of budgeting and stuff like this. But in terms, when we discuss with the team and they say, oh, okay, I actually would like to have our workload running on Swift. I mean, for them, it's kind of a free offering. And with the free offering, I mean, we probably have seen also, I mean, you run sometimes into many issues in terms of usage, right? I mean, customers start using it. There's a burst number of requests. There's uncontrolled usage. And of course, I mean, if the quota is not set, I mean, sometimes customer, even though they estimate they're going to be using, let's say, 1 petabyte, they end up, you know, in one day using 2 petabytes or something like this. So what we had to do in order to mitigate that, we had to definitely, I mean, provide a full quality of service. So part of the QoS, I mean, we had a controlled request per second. So we have usually, I mean, an engagement with our customer. We try to understand kind of what they need to do. We try to direct them into the right solution. And then we kind of, depending on their use case, we kind of discuss about certain requests per second limit. And also we discuss about certain throughput that we allow them. If we feel at some point, when they start running, they're kind of, reaching close to this limit, we discuss about them, how either they have to optimize their workload or what we can do on our side, to allow them more and to increase basically the offering to allow more towards, for them. And the last thing, of course, we implemented part of Swiss is what we call an account quota management. This one we had to be very careful because, many of the workloads, they start storing objects on Swift, and they sometimes, our customer doesn't know how much, they have quota left, or so we try basically to monitor that for them, and when they reach a certain limit, we kind of notify them. We work with them about either for them to get approval for additional quota, or kind of if there's any way, for them to clean up their data in order to get within the original storage agreement quota that they had. The third challenge is related mainly to concurrent requests about the same object. And why this is a challenge? Actually, this is a big thing. Especially some of the use case we had when I'm discussing about deployment. Let's say, you have a jar, you want to deploy it into, I don't know, thousands and thousands of VMs. So think about thousands and thousands of VMs. They're having basically GET request almost at the same time in order to get the object, right? So what you end up basically with the solution that I was describing earlier, especially because your object is on a spindle, right? So you're getting so many requests, and at some point, the spindle, cannot handle all of them. So at some point, those requests are just timing out, they're failing, et cetera, et cetera. So we had definitely, to find out a solution for those type of use cases. So what we did, we used what we call varnish cache. Some of you may be familiar with. Also, we use it kind of, as an open source solution. So we provided right after, the software load balancer. So depending on the request, some of them are directed to varnish cache. And if the varnish cache basically is not able to retrieve or does not have the data, it's going to retrieve it from source. So at least in this case, basically, when you have a huge burst of same request, once varnish cache is able to get the data from Swift, it's going to be able to respond with all subsequent requests, with this data. So this definitely helped. The other thing, that we work with our customer depending on the size of the object is what I call chunking. So let's say, they have an object size of like 2 gig, 3 gig. We discussed with them about kind of providing multiple kind of chunks of the same object and assemble them with a manifest. This is not something I'm going to talk in detail in today's session, but if you guys are interested, there's something in Swift called a large object. There's dynamic large object handling and static large object handling. Swift basically handle anyway maximum of 5 gig. So those strategies are used, to handle large object. But we were able to use it even on a smaller objects as well. The last challenge is, the challenge number 4 is related to geo availability. And what I mean by that is, as you know, eBay is kind of almost worldwide, and we needed to ensure that either from an upload or from a download perspective, our customers are getting the best performance and are getting basically endpoint that are closest to their location as well. And of course, we had to provide a solution that is very highly available, and also that provide a solution that provides disaster recovery as well. So in this case, I'm going to talk about one of the deployment solution, Replica 3. What we did in order to provide that. So imagine basically 3 data centers. They're located, I mean, multiple locations, maybe 2 in US, 1 somewhere else. And then what you have, I mean, similar to what I discussed before. So here you have the SLB, you have the cache, the varnish cache, the Swift proxy, which is, I mean, the pack node, and the Swift object. And when a request is received, basically is received kind of by, I mean, the end user sent the request to the GTM. The GTM is going to respond with the closest point. But of course, I mean, here I mentioned Keystone. So we use mainly Keystone for the identity as an identity service. So the end user will have to call Keystone, get a token, which is valid for X number of hours or days. And then basically when the end user have their token, they're able to call Swift and access an object or store an object on it. Challenge number 5, this is the before last challenge I'm going to discuss. So again, multi-tenancy and zone isolation. So multi-tenancy, I mean, think of it as you have basically, I mean, again, we have 900 accounts. So we had to ensure basically all of them works in isolation. But also what I mean by multi-zone, so we have one huge Swift cluster that we call Swift Global, and this Swift Global is provided on staging, is provided on sandbox, is provided on production, is provided on the analytics zone, et cetera, et cetera. So we had to ensure that definitely there's no data breach. Only the user who have access to a certain account within a certain zone kind of stay within this zone and stay within this account. So what we did, we implemented basically multiple middleware on top of Swift. And those middleware provided us with the level of isolation that is required, I mean, by the business. I'm going to talk briefly about one of them. Which is related to the zone isolation. So one of the way, I mean, we did that is, I mean, from Keystone, we were able to, whenever a user is calling Keystone or the identity service to get a token, we were able to inject the IP address of the user part of the token. But also in Keystone identity service, we modified it in order to ensure that Keystone does the validation that the end user who's requesting a token, let's say for production, is already approved and running part of production environment. So we validate the IP, again, the subnet, a list that basically shared with us, and in order to ensure that this user is allowed to get the token, I mean, he's requesting. So once the token is created for this end user, Swift receives this token, and Swift again does the validation to ensure that the IP is the same IP that was included in the token. No, I mean, it's not like the end user, I mean, generated the token from running on one machine, and now he's using it from a different zone, from a different machine. So we validate that. And once we validate this information, we allow the end user to access the account. Of course, I mean, we have to do validation on the account level as well. So this is one of the middleware, I mean, we implemented in eBay to provide zone-related isolation. The last challenge, basically, I'm going to talk about today is related to, think of it about backup and archival. And many of you probably, I mean, is facing that. I mean, especially the question, oh, okay, I mean, we have data in warm storage now, kind of, I mean, the data, I mean, either, I mean, need to be in cold storage, or more kind of, I mean, I know kind of I need to shift a huge amount of data, basically, but I'm going maybe to access it very little, or I mean, in the future, just in term of archival. So, and for those type of use cases, definitely, I mean, you need you need the cheapest solution. I mean, you need also high durability. I mean, you don't want to lose the data, but also at the same time, you want to make sure, because also, I mean, you have a huge amount of data and you're not accessing it much. I mean, you're not paying, I mean, very high price in terms of storage cost. So Swift was used as one of the solution for those type of use cases. And in order to leverage Swift, so earlier I talked basically about Swift in a replication policy mode. So here we used what we call erasure coding. And so we were able to get 175% less storage overhead with the erasure coding solution policies we provided. And again, I mean, so it's still part of the same Swift cluster. Depending on the account or depending on the container, you can say, oh, actually, I want to apply the archival storage policy, and so you're going to get basically the erasure coding applied, or I want to apply, I mean, the regular standard high performance policy, and you're going to get basically different type of, I mean, more into replication type of solution for your request. Okay. Now we talked challenges, we talked solution. The last part of the presentation, I would like to focus a little bit on running Swift. I mean, again, I mean, it has been a great experience, but definitely we couldn't done it without, I mean, of course, I mean, the storage team who kind of, I mean, helped greatly kind of with those implementation and running the day-to-day activities on Swift, but also we couldn't do it with the large tooling around monitoring and alerting that the team provided. And this is a key area, actually, in order to run large, high-quality production cluster. I mean, pretty much, I mean, any type of cluster. Here I'm going to discuss briefly about what we use, some of the solutions, I mean, we used, I mean, for Swift. So definitely ELK, Elasticsearch Kibana. I mean, this is one of the key alerting, I mean, monitoring solution. I mean, we had in place. We implemented that with Prometheus as well. We had our own synthetic tests, so we're doing periodic tests and we're doing validation on ensuring basically the health of the system. We're not only relying on kind of passive monitoring, we're actively ensuring that the system is healthy. We use also Zabbix and all kind of additional type of metrics. So here I'm going to show some of the screenshots. I mean, this one probably recognize it. I mean, ELK. This one is providing some stats around. I mean, the first one, think of it as about. I mean, the zone. The second is around the accounts usage, and then you have information about. I mean, each account, I mean, you can drill down, you can have each account, okay, how many containers, et cetera, or at a global level, I mean, how many containers, how many objects. So you can drill down for each account. And this one is very helpful, I mean, as in terms of metrics or kind of informational status. And we have alerting set on this, especially because when we discuss with our end user and we discuss about their use case, we set a quota for them. And once they're kind of getting close to this quota, I mean, we start sending alerts. And so through that, we're able, basically, we have specific alerts in order to, that are fired based on the account and based on what we agreed with the end users. The second area, which probably, I mean, more interesting for you guys, is what I call what's going on the Swift cluster in terms of requests per second. I mean, so here we record all the requests that we receive, either GET or PUT, et cetera, and we analyze the flow, we analyze the usage, I mean, the pattern, et cetera. We also basically do the analysis if there is certain type of errors that are being sent, is either 500x or 400x. If we see an increase in either one, kind of, I mean, there's alerts, and there are basically notification that are, I mean, that we receive. We start checking if there's any issue either on our system, or this is basically kind of benign, someone is doing some test. So we closely monitor and follow up on those. And the last slide, actually, I'm going to talk about. Earlier, I mentioned part of the monitoring and alerting. We have our own active tests. So what we do, we set up automated testing. We upload files, we download them from multiple locations. We have different sizes, et cetera, and we analyze all of that. I mean, part of this graph. Anything that is basically not specific to the norm, we generate an alert. We start looking into what's going on, if there is any issue on our side, or this is a benign, basically, problem that we're seeing. Great. Thanks a lot, everyone. I would like, I'll be happy to answer any questions if you have.
Thanks.
Do you see any demand for low latency object storage?
Low latency?
Yeah.
Yeah. I mean, definitely we have many use cases that are, I want to say, in an average latency. So currently we provide two type of policy. One we call kind of high performance, and the other one we call basically archival. I mean, definitely archival is very low latency. I mean, here. I mean, in terms of, if you think about the high performance, this is something we try to have our SLA within certain millisecond commitment. There has been discussion if we want to kind of provide a third one kind of in between. So let's say, for example, for the high performance, your SLA are kind of smaller than 5 milliseconds or so. I mean, for your archival, maybe they're into the 30 or more, something in between. This hasn't materialized for us yet, but definitely there has been some consideration on that.
What about something that would be like sub-millisecond?
Sub-millisecond. Good question. I mean, this one, I mean, definitely we have some specific use cases that are into this category. Currently, we're not leveraging object storage for them. Yeah, but definitely, I mean, there is a good point, and kind of, there has been certain use cases where, whenever it's millisecond or under, we're kind of, oh, okay. I mean, definitely, it's not on our. I mean, we're not going to handle it right now. Who knows in the future? But definitely there can be.
Okay, you presented 6 challenges.
Yes.
And 6 solutions.
Yes.
Which one of these solutions gave you the best bug for performance?
For performance, basically.
Performance.
You know, I want to say, I mean, 2 things. One is related to the caching, where we implemented basically varnish cache. And the other one is related to the first challenge that I discussed about, related to when we have a huge number of requests, and we split down basically the Swift PACO nodes in proxy nodes or PAC nodes, and then object nodes. Those provided the best, basically, performance, I mean, for our end users. Sure.
What's the level of object churn in your environment, and how do you measure it?
Good question. I mean, I don't have, I mean, the data, I mean, with just to make sure, I mean, when you're referring, I mean, object churn kind of, I mean, when you say object basically replacement and
Yeah, well, object store, by definition, it's write once, right?
yeah, exactly.
So object churn, I'm defining as object is no longer needed, so someone's actually
Yes.
executing a delete operation
Yes.
on the object.
Yeah.
And
Yeah. So this is a good point. I can explain to you how we handle it currently, and I'll give you some numbers or kind of, I mean, some high level. So currently we have two options. I mean, we have what we call a retention program. In Swift, I mean, you can set up basically a delete at. And you can say, oh, I'm uploading an object, and I want to delete this object after 3 months. So you could automatically set. Or the other option is basically, I mean, when we work with our end users, they don't know exactly when they want to delete, but always we kind of suggest to them, if they don't know, for them to kind of always assess and work on, okay, I mean, if this object is still in use, and if not, I mean, for them to have kind of, I mean, the deletion apply for it. And this period in terms of, like, I mean, retention, I mean, can vary a lot. I mean, for example, I mean, one area I talked about is PCI, PII. This one, by security audit, we have to keep the data, I mean, within, I mean, we cannot delete it, I mean, within a certain. Other zone, I mean, they have different requirements. And of course, other use cases have different requirements as well.
I might have missed it in the PowerPoint, but where in the system are you executing rate limiting? Is it in the proxy layer, or is it in the
It's in the middleware,
load balance?
middleware, Swift middleware.
Oh, okay.
Yeah. So we implemented our own middleware in order to have the request per second limit, and also we have also the throughput. We have it part of the middleware. I mean, but of course, I mean, this middleware is relying on other system in order to, because think of it, I mean, Swift is stateless, right? So a request can be received by one proxy, but the other request, I mean, by another proxy, et cetera, et cetera. So we had to ensure basically we have the information from all systems.
And that's defined per account?
It's defined per account, yes.
Okay.
Hey, thank you for the talk.
Sure.
I'm more interested to find out your choice of going with Swift as opposed to Ceph, which is another big object storage. And any of these challenges that you listed, does Swift perform better? Is it because of just its integration with OpenStack? What was the decision?
Absolutely. I mean, again, eBay is a big company. We have Ceph as well. I mean, we use less Ceph on the object storage side. We use it more kind of, I mean, for I mean, either file system or block storage, I would say. I mean, the main decision, I mean, when we analyzed it in 2014, Swift was at a certain maturity back then, and that's how kind of when we started introducing them. I know kind of, I mean, Ceph has been doing a lot of catch up, and now it's I mean, I didn't try it, I mean, lately, but I have been reading that it's becoming, many of the features that were only provided with Swift now exist also on Ceph object storage or object storage solution. So definitely right now there could be a consideration, I mean, for Ceph.
Other questions over here?
So you had mentioned the few previous object storage you'd gone through, right? I'm just curious, how much of that was planned versus reactionary? Like, was it not meeting your needs?
Fair question. So again, one thing, I joined eBay in 2014 when we introduced. So definitely many of the elements I presented, I got some historical from the team that were there. I mean, my understanding, I mean, at some point, I mean, from the team, especially when they introduced the eBay picture service, at some point, I mean, they had a really huge issue in terms of scalability, and the site was growing, the demand was growing, and they didn't know how to handle kind of, I mean, this huge growing amount of data storage. And that's kind of, I mean, where they discussed and they had kind of, I mean, I felt, yeah, I mean, at that point it was, oh, okay, I mean, how we can solve it, I mean, right away. Then Atmos was introduced right after. I mean, again, it was the early stages of object storage, right? I mean, back then, 2007, AWS S3, I mean, was in a beta also, you know? So it was very, very early stages. Now I mean, then there was basically planning, and zStore was definitely created out of a planning and visionary or kind of, I mean, vision in order, oh, okay, I mean, we want to definitely solve the problem the right way, and that's how zStore was introduced, and we were able to get kind of, I mean, to move away from the eBay picture service. And also, I mean, discussing further, I mean, with Atmos, we had kind of, I mean, many issues I didn't describe or talked about here. But also, I mean, when we introduced Swift, it was about, okay, the next object storage solution, and definitely we want to move away from Atmos related. And we were able to achieve that, I mean, a few years ago.
One more question, somebody? No? I think it's good.
Thank you. Thank you, everyone.
Okay, just a quick update. The Emerald spec that I talked about earlier is now an ISO standard. You can go out and see it out there. And I'd also like Tom Coughlin to give us some short remarks on IEEE before we go to break.
Thanks, Mark. Yeah, so I'm Tom Coughlin. I'm the president this year of IEEE USA, and I just wanted to let you guys know, really appreciate the opportunity to work with you. As IEEE in general, I think it's really important to have strong industry connections, including with trade groups and that sort of thing. So that's basically what I want to say. And also, I wanted to apologize for all of you who are not able to get a copy of our engineering crossword puzzles or the engineering coloring book. Come to some other event, we'll have some of these. Thank you.
All right, we're on break till 10:40. Come back at that time. Hope you all got your coffee and muffins. Our next speaker is Eric Rees from Toshiba Memory. He joined Toshiba Memory in 2013 as a general manager of corporate development and strategy for semiconductor and storage products company in Tokyo, and then returned to the U.S. in 2016 as senior vice president for memory and storage strategy. The Memory and Storage Strategy Group explores methods and technologies to better integrate memory with storage and storage with software. The mission is to create a more compelling and fluid way to manage data in a world where systems are now scaled and integrated in an unprecedented manner. Please welcome Eric.
Thank you, Mark, for that kind introduction. And it is my pleasure to be able to talk to you all today. And I appreciate SNIA organizing this conference and giving me this opportunity to share some thoughts with you, particularly how at Toshiba Memory we're working to be a driving transformational force in storage. And with that introduction, first things first, I do have an announcement for you all here today. And I'll hark back a little bit to what Mark said. I hailed here originally from the Tokyo headquarters where I was part of what we called the semiconductor and storage company. And that was part of this big conglomerate called Toshiba Corporation. And we could provide you nuclear plants and we could provide you NAND flash and a lot of things in between. Well, all good things have to come to an end. And last year, Toshiba Memory spun out from Toshiba Corporation. And it's been our distinct honor to be able to carry that Toshiba label, that Toshiba brand, for another year while we got ourselves organized. Well, next week on October 1st, our name is going to change. And hopefully, after I unveil our name to you, if you haven't read it in the press already, it'll make a little bit of sense to you on where we're going to be going in the future. But drum roll, please. Our name will be Kioxia Corporation. I heard a giggle already, so. I challenge any of you to say this as fast as you can, well, 10 times in 5 seconds and see if it comes natural. Hopefully it will. The name actually has some good thought behind it. We're a Japanese corporation, and so we need to maintain some of that heritage. So our name combines a Japanese name for memory, or Japanese word for memory, and in the Japanese language there's multiple words that are available to express memory. But one of those is this one, which is kyoku. And kyoku embodies memory in a broader sense, and more in a humanistic sense. And we've combined that with the Greek word axia for value. If you don't mind me getting serious for a moment here, and I'll share a personal thought. Some of you may share this, but my mother suffers from debilitative memory issues. And one very sad thing about that is, sorry, this is a downer. I'm supposed to be an upbeat speech here. But you lose your identity over time because your memories are part of your identity. And those memories bring value to who you are and what you do. And that's the same for a human being as it is for a corporation, it is for anything. And that's what we're trying to express in our name, not debilitative disease, but actually the value that memory brings to our lives and to the things that we do. And that's why we're using the word kyoku as part of our name, kyokusha, to show to the world and to ourselves that we are embodying the value of memory and what that brings to ourselves, what that will bring to you. And also that we will continue researching into the areas of memory beyond just simple NAND flash. So, for you Monty Python fans out there, now for something completely different. Silly walk? No, I won't do the silly walk, I'm sorry. But we can do the argument one if you want. My legal department took all the fun out of here. I wanted to have one of those Terry Gilliam animations, particularly the one where there's this guy's bird head, and this guy's coming like a bird out of a nest with his head open like a clamshell. And there's this fish flying along into his mouth. And that fish was going to have the word enterprise on it, because the cloud is taking over enterprise and the guy was going to be the cloud. But instead, we'll have to go with the fish and the shark here. But the idea that my legal team quashed, but we still, I think, achieved through this animation or through this illustration, is that data centers are in motion. Our electronic world is in motion. And there's a shift going on. Not too many years ago, I guess I shouldn't use names, but there was big corporations that that embodied the idea of storage, and that was in that enterprise area. Now we're moving where cloud is really taking over so many things that we do. And the traditional dichotomy of enterprise storage versus the other stuff is going away, where that other stuff is going to be public, private, oops, sorry for the preview there. Private, hybrid, and other things. They'll coexist, but in a slightly different nature. Another good thing about this illustration is enterprise up until now has been this big, powerful thing that dominated. I don't know if carnivore is the right image or not, I don't know. But big and powerful presence within storage. But we have all these little fish, these little things that are coming together as that cloud. And to continue to abuse this metaphor, even though they look huge and imposing and are scaring the shark away, any of those individually can't take the shark out. And as a group, they really can't take the shark out. They can overwhelm it, disorient it. And I don't want to abuse it so far to say that the cloud is going to disorient and abuse mentally abuse a shark. But things are changing, and it's no longer going to be the #1 dominant thing in the world. And this graph hopefully will show that. This is looking at data traffic, cloud versus traditional data center. And even in the historical realm here to this future forecast, the amount of traffic just isn't even comparable, and it's growing very quickly, up to where we have, what, 20,000 or so exabytes of data that's going to be flying around. Now, some of that's going to have to be stored. Probably a lot of it will have to be stored. Some will go into permanent storage, some will be hot, some will be medium, and whatever we decide, whatever you developers decide to categorize it as. But that will be stored. And the majority of those exabytes, be they hard drives or hopefully flash in our case, they're going to be going to the cloud vendors. That's just the way it's going to be. It's no longer going to be the enterprise that's going to be driving all of that. And when I break that down into flash itself, well, the cloud is going to be, according to Forward Insights, by 2023, roughly 60% of the bytes that are going to be shipped in flash will be going to the cloud. Kudos to the enterprise guys. They're still there. They're still significant, but the driving force has shifted to the cloud. Now, of that, I'm going to now ask you to forget about the fish metaphor. That cloud is not made up of a bunch of little guys. There's actually 3 or 4 really big guys and then a lot of little guys. And those big guys are what we like to call, in the most friendly terms, hyperscalers. And most of those bytes are going to be going to hyperscale. And one other thing about our friends, the hyperscalers, they don't use storage the same way that has been traditionally used. The hyperscale cloud storage paradigm is application-driven, software-defined. And the drives that my company is shipping today, that my competitors are shipping today, are not necessarily of that nature. Sorry, I missed a slide here. Not necessarily of that nature. But there is that gap. The industry hasn't filled it. And so the hyperscalers have taken it on their own and begin to define. They have, I shouldn't say begun, they have been defining their own storage devices. And in some cases, they've been building their own, because their usage model is different. These devices, they're host controlled, they're application driven, and highly integrated into the stack. With the typical SATA drive, that may be difficult for you to do right now. Thus the new definition. Another reason for them doing this is flash continues to grow in its share of the storage that's being used by the hyperscale providers. There is a lot of flash unique processes that impact their business. Some of these processes are garbage collection, data placement, and wear leveling. Each of these play a different role in affecting the quality of service or the value or the service that the hyperscaler can deliver. In the old world of the spinning disk, latency was a pretty consistent thing that could be planned for. Unfortunately, with solid state storage, it's not quite that way. Schrodinger's cat likes to pop out every once in a while and confuse things. Or more typically, the drive has to go do some business and then it'll come back online. Data placement as well. As you're architecting your software and your applications, you categorize your data in certain ways and you need to place that in an environment where you'll get it back predictably. So these are all elements that we've noticed in the hyperscale world are very important and that need to become more available to the developer. And I'm not telling you anything that you don't already know. I've had these conversations on the side with many people, but it's always kind of been this why can't they, why won't it be world. And as hyperscalers are pushing the envelope in one area, our storage as a device has been continuing to evolve in its own pace. For so long, it's been just rotating rust. Let me go down memory lane a little bit with you. And I will be betraying my age a little bit here. But there was once that day when the first hard drive, well, this one precedes me a little bit. The first hard drive was developed by IBM. And when you wanted to move it from location A to location B, you had to put it on an airplane with the forklift and then take it off with the forklift. And I think that was 5 megabytes. Is that right, Scott? Eventually that transferred into something that I remember, which is a cassette deck. I remember my friends and I playing around with Commodores and recording our routines on a cassette deck, and then that moved to a 5 1/4 inch floppy, and then a 2.5 inch cassette, and on we go. But the consistency here that I want to pull this back into the theme is that there is all some kind of media, magnetic-based media that was being manipulated. And that created a bottleneck because you had to translate things to be able to get it magnetized, and then you had to read it back and you had to translate it back. And in storage, there was, in our recent lifetime, an extremely innovative change, and that was when NAND flash was turned into a drive. Then all of a sudden, the great wish that everybody had of why can't my media move at the same speed as my interface, that happened. Actually, the media can move faster than your interface. And I think many of you probably joined me in rushing out to the store to get the first SSD that you could put into your PC, and wow, all of a sudden your PC moved faster. And that happened in the data center, and that happened every place else. Well, in the hyperscale world, and they're leading us, and when the rest of us will catch up there, they're already saying, this interface is too slow. Why can't my application move at the same speed as the media? And unfortunately today, solid state storage, although it is digital, it can move faster, we're still having to deliver it as a drive. It still has to behave as a drive. And all of that implies both the good and the bad. The good being also consistency, standardization, call out to the standards group that has performed this, put this thing together. And lest I be misunderstood, today's speech is not a call against standards. Definitely not. But a fresh look at the paradigm that solid state storage must be enabled for software control. It's digital, your world is digital, they need to come together. And guess what? The hyperscale guys are already doing that. We've already talked about how they're defining their own drives, their own way of doing things. And it is to take advantage of that digital nature, or to put it another way, to take away the roadblock that that is there because they have to pretend you're a drive. So we as storage vendors need to pay attention to that, and today is kind of a call out for us to be able to do so and to start doing so, and to you as developers to push us to keep doing that. And the cloud is continuing to push innovation. We'll push it in storage. It's pushing it in our lives. We see it in analytics. We see it in finance. And please forgive me for using such a popular buzzword, but it's even AI. I really fought putting AI on there because it seems like everywhere you go, every startup has something that has to do with AI. But AI is here to stay, and it is driving innovation. It's driving it in the cloud. It's going to be persistent in the cloud. So to bring this back a little bit, innovation is pushing, cloud is changing things. The hyperscalers are really leading that. But still today, the drives are defining their own way of their own mode of access, where we have a standard, we have an interface. That interface defines the system and onward. But really, the cloud operators are requiring and demanding that the applications now be able to define how data is stored. Go back to those elements that I talked about before with where leveling and garbage collection, but most importantly, data placement. And that the reason why is because this, as I've alluded to earlier, affects their business and their ability to deliver a good quality of business. These things, oh, keep hitting the wrong button, I'm sorry about that. These things that we kind of put in the bucket of orchestration, being parallelism, predictable latency, data placement, these things are all important elements in being able to define how the data can come in and come out and be done in a predictable way in a cloud environment. And this is where we have seen the hyperscale people are innovating with their storage, with their self-defined storage. Obviously, I can't, in a public domain, talk about the specifics that come our way, but these elements are all impacted by the definitions that we have the privilege of seeing. So, solid-state devices are digital, and these features that I have listed here should be able to be and can, from a technical perspective, be managed at the storage level through the application. And so much of this right now, I shouldn't say much of it, in a standard drive right now, these things are defined and delivered through a proprietary firmware program that is installed with the drive. And because it's proprietary, because it's firmware, the hyperscale environment, as the applications run, cannot reach down into the drive and say, "Thou shalt not garbage collect right now. Please wait till I'm done with this routine." The firmware is going to say something with an index on their hand, and now I'm going to do my garbage collection right now, whether you like it or not. So with this, as developers, you know that we have this new paradigm that is coming. The application really does need to be king in driving how the storage is going to be done, how it's going to be written, how it's going to be read. And we, as solid-state storage manufacturers and deliverers, need to be paying attention to this, and not pay attention to, but I would say embrace it. Cloud-based applications are the new normal and will continue to drive innovation. I'd like to share with you now, on the next slide, a kind of a little wistful, wouldn't it be nice to, set of ideas and somewhat of a industry call to action. But future versions of software-enabled storage should be able to, or wouldn't it be nice if they could support the following? Why couldn't you have a somewhat amorphous pool of storage that you could reach to with your software, that you could aggregate it based upon your workload, and you could deaggregate it based upon the workload needed? I've got a heavy one coming, I need a big pool. The second, why wouldn't you be able to say, of this pool, I want to be able to run one routine based on one standard and one on the other, and be able to do that simultaneously, and be able to have these capabilities and functionalities running simultaneously on this quanta of storage that you've been able to aggregate based upon your application and workload need, and be able to therefore, in so doing, control the latency in a deterministic fashion that fits what you need for that workload, for that routine. finally, as you're doing this, for the host to be able to say, okay, garbage collection will happen on this cadence. Wear leveling, we're going to hold that off for a while until this particular heavy workload is done, then we're going to go ahead and wear level everything out. So these are some of the quirky things of Flash that if you can control, we can take away that bottleneck of having to look like a drive and really open up storage to something that can be fully digitized and fully orchestrated according to the needs of what you're developing. So I'm going to kind of wind up one phase of this and move into another phase. The cloud is eating into the enterprise. I don't think anybody would argue this point. And the hyperscale cloud is dominant in that fashion, and they are software driven. And from a storage perspective, their application is king. This is the new paradigm that is coming, forthcoming. It's nipping at our heels, and something that I think we need to be able to embrace. And as I've alluded to before, I don't think I'm telling you anything that's brand new. I know I've had many of these wistful conversations in the past, but I do believe that this is something that now is at our door, something that we actually can begin to deliver in the near future. So at Toshiba Memory, soon to be Kioxia, we are exploring new ways how to make Flash more valuable in the software-defined world. So I said I'm going to shift phases here. So the phase was, where do we need to be going? What's the paradigm? What do we need to be doing? I'm going to be talking about now, with today's technology that we have now, how by embracing software into the storage area, into the storage device world, how can we increase the storage value? So I'm going to share two examples. One that I will, this is my own term, say is a drive-aware software. It's an actual product that we announced late last year. And the other one is software that we've worked on that is what I'm calling media-aware. And each of these, there's different things that you can bring to forward, different forms of value that can be brought forth by having either your software be drive-aware or media-aware. So let me talk a little bit about a software that we released last year called Kumo Scale. And Kumo Scale is software that deploys SSDs at cloud scale, and it also enables NVMe Flash as a service. Kumo is a word in Japanese, has different meanings. You'll see the Chinese characters next to them, but one is a cloud, and with the same pronunciation means a spider. See some Japanese people in the audience. Probably if you pronounce it a little bit different, you might be able to hear it, but to us Anglophiles, it sounds the same. One is a cloud, one's a spider, and you'll see why we picked this name as we go through the product. But Kumo Scale is a product that implements fast networked block storage as a service that is based on the NVMe over Fabric standard. It's architected to be able to work well in these modern container orchestrated systems, as well as the more conventional bare metal environments. Also, Kumo Scale, as the name implies, is built for scale, and it makes NVMe Flash more efficient, more cost effective, and easier to deploy at scale, at any scale. Also, it's targeted for the on-premise cloud with compute nodes roughly 50,000 to 500,000 in size. And the primary purpose here is for a private network to be able to provide NVMe Flash as a service. Let me talk a little bit about the architecture here. Pardon me as I build out the slide. Okay. So I'm going to explain what we call the Kumo Scale node, and this is the workhorse part of this particular product. So requests will come in from the network using NVMe OF commands. A namespace will be assigned, and that'll go into a mapper. This mapper then will map it out, convert the commands into NVMe, and then assign a physical drive. So this will be how the data path is set up. Once the data path is assigned, Kumoscale steps out of the way and will not be involved in any of the data, will not be involved in the data path. Sitting on top of that on the user side, so first was kernel level, now we're on the user side. There is a management engine that will be talking with your provisioning and orchestration frameworks as well as the telemetry and logging frameworks. Those will come in via telemetry and other functions. Then what happens in the mapper will be brought up into the engine and back and forth, and this will then connect with your overall systems. When you translate that into the overall environment, from the provisioning or orchestration side, requests will come through. Those will go down to a mapping, come into the Kumoscale node, and the functions I described will be executed. On the blue lines here on the left, you'll see the data path will be established. Then telemetry will come back into an analytics service that will then modify those nodes of n amount. And we'll be looking at drive health, drive endurance, and other things, and we'll orchestrate the mapping accordingly, and we'll feed that into the analytics source, which will then be brought back up into your provisioning tools. Also within the analytics area, there will be other health-related information that I talked about earlier that will come over to your management service, and based upon the design, there's a phone home feature that can send that data back into your other systems, your administrative systems, to be able to either look at your license usage, whether new drives need to be provisioned, and other things like that. So that's fast. If you want to learn more, we have some people here on the floor that can talk to you a little bit more, can explain a little bit more to that. Today, my purpose is just to show that in this way, if you're aware of how an SSD works, what its quirks are, what its strengths are versus its weaknesses, you can orchestrate a system like this that will stay out of your data path, but still allow you to deploy the drives in a much more efficient, cost-effective, and durable way. So that's first example number one, the drive-aware software. Let me talk a little bit about the second, which is the media-aware. In this case, I'm saying media-aware for better total cost of ownership. But certainly, with your creative minds, other values could be brought into place if your software is developed in a media-aware fashion. So we call this TRoxDB for Toshiba RoxDB. If any of you are curious, we're not going to call it KRox we're going to stick with the TRox name. But I'm sure everybody here is familiar with RoxDB. It's one of the more popular open source database engines, and is used in a lot of these databases that are listed here. RoxDB of itself has a history that goes back to Google. I think Facebook is the primary promoter of it right now. It's a very good piece of software. So I do want to be clear, what I'm going to talk about now is not in any way knocking RoxDB. We're actually trying to make it even better, from something that's good to better. Particularly with a hard drive environment with small database values, RoxDB as it is works great. However, if you deploy it into flash media or into solid state storage, there are some issues where greater value can be brought forth if this is modified to take into account some of the quirkiness of solid state storage. Particularly the way RoxDB is architected now, with a hard drive, it doesn't matter how many times you rewrite your data, it's not going to wear it out. Unfortunately, with a flash drive, if you keep rewriting data, you're going to wear it out. And RoxDB, as it stands right now, in the compaction process, will rewrite things enough so you get a write amp of up to as high as 30 times. So there is a better way. And we spent some time, I don't know if any of you attended Remington's breakout session. He's up here in front, you're welcome to talk to him after. But we did spend some time going through the code and saying, oh, how can we do this in a more flash-aware, flash-friendly way? Sorry, that's a tongue twister. And I think we're able to do so completely in software, no changes necessary to the SSD. Let me make one comment that I forgot about on Kumoscale. For Kumoscale and TRox, in both cases, it will work with any SSD. We're not going to tie you to a Toshiba or soon to be Kioxia drive. You can use it on any of them. In the case of Kumo scale, if you do use a Toshiba memory SSD, there are some added features, some other value adds that we can give you, but it'll work just fine with the Company S or any other SSD. And the same is true with T-ROX DB. You can use it with any SSD. So with that in mind, let me walk you through what it is. Here on the left, we have RoxDB as it is today, as it's commonly shipped, and that the keys and the values in the database are stored together, and they're rewritten together as it goes through different compaction layers. And as I alluded to earlier, that will result in a high level of write amplification, which is, to use one of our teammates' expression, SSD abuse. On the right-hand side, you'll see here that what we've done, and let me build this slide out now. With T-ROX DB, we've separated the keys and the values. The key, obviously, taking an insignificant amount of memory, can go through each compaction layer and travel with that. But what we've done is we've put the values in a ring buffer and held those at the side so that they are there and they are not rewritten unless there's an event that demands some update of that value. And here at the bottom, there's a release old data function that allows that update to take place. But saving that, the data will stay as it is, and the database performance functions without creating excessive write amplification. So by being cognizant of media characteristics, developers can enhance or produce greater value within the storage. In this case, you can extend the lifetime of your SSDs. And this can be done, in this case, we've done this with no impact on performance. So when I kicked this off with our team, that was one of the requirements that I said is do not impact performance. Nobody's going to use this if the performance gets bad. And here's some data to show it. We've run multiple tests. Here on the far side is the write amplification. And you'll see the various test modes that we ran that under. And in the worst case, we had we had greater than 50% improvement in the worst case, and in the best case, significantly more. If you look at performance, the worst case was on par performance, and in the best case, although not as dramatic as write amplification, still, when you look at the random key reads, significant improvement in performance. So again, not to beat a dead horse, but if you look at what are the verities, what are the strengths of the media and the drives, there is value with today's things that can be extracted and can be presented to your customers, to your efforts, by making the software more aware of how a flash solid-state drive or solid-state media performs. In the case of T-ROX DB, we've made this open source. There's our GitHub address. We have in our table out in the lobby some takeaways that also have the GitHub address. I definitely would encourage any of you that are so inclined to join our project, improve, and contribute to the code, and help your solid-state storage get even more better. I had a term that probably isn't good for public consumption in my mind. So I want to conclude here and wind things up that, calling back to the beginning, there is a new paradigm shift. The cloud, our world, AI, and other things are really driving innovation in a level that I went from seeing things from cassette decks to, carrying everything in my pocket now. So, I mean, that's pretty dramatic progress, but it still seems to feel like it's accelerating, and I believe it is. And where we used to have a media bottleneck, now we have an interface bottleneck. And we have a form of storage that's digital. Why not combine it with your software efforts and really be able to extract the full value? And hopefully, with our modest efforts and showing some examples from Kumo Scale and T-ROX DB, that'll give you an idea of what can be done, plus more. And in all of that, solid-state storage has a big role to play. After all, it's digital, and it's cheap. But don't tell my CEO I said that. So all we need to do is, and I shouldn't say all, let's say, It's a big ask, but we need to make our solid-state media more software-enabled. So as I wind this up, I'll just say that this is an area for Toshiba memory that is important to us. We're spending time on it, and we are investing in it, both in terms of software and of media. So I've shown 2 examples of what we're doing with software, and we're doing more. We do have other projects underway and in works. And we're also exploring ways that we can make the media more capable of interacting with the software in a more direct fashion, so that we can help move into that new paradigm that we're talking about. I don't have anything I can share with you yet. I hope that there is a time in the future that I can share that with you. In the meantime, happy coding. Thank you very much.
Questions?
Scott Stetzer.
You mentioned that the...
Just a second, I need to bring one of my staff members up here. Scott, would you come over and join me on the stage? I want to introduce Scott Stetzer. He's been one of the leads in everything we've been doing. I have a liberal arts degree, so if your question is too technical, I'll kick it to him. If it's conceptual, I'll own it, but please.
You mentioned that the hyperscalers are driving a lot of the innovation compared to the mobile market.
Uh-huh.
To what degree do hyperscalers drive innovation versus the mobile market drive innovation?
That's an interesting question. You know, I wrote this presentation from the perspective of mass storage, and definitely that is hyperscale driven. Within our own memory division, there has been a tremendous amount of innovation in storage, but that has been uniquely with how we deliver a flash in a more discrete fashion. So there have been a lot of innovations around the interface, around the physical nature of that. But I would say not, when you're looking simply at solid state storage, not as dramatic as what we've talked about today. I can hearken to one particular effort that we had in making the memory within a smartphone more directly accessible to the OS. But what we've seen is that becomes a tremendously siloed effort, and it doesn't really cross-pollinate to others, where in the hyperscale environment we're seeing that the technology tends to spread itself across the industry much more quickly. It's my opinion. Anything to add, Scott? No? Okay, thank you. Any other questions?
Hello. So just now you mentioned that you are working on the T-RocksDB. I was aware that there was another work called Whiskey.
Whiskey, yes.
Yeah, which based on LevelDB.
Yes,
I think
Whiskey,
that here it's the same, right?
Whiskey was a key element that we referred to, and actually I think if Remington would have referred to that. We actually talked to the people in that university that gave us some ideas. Whiskey, without getting into the details, does attempt to solve a different problem than what we're trying to solve, but the methodologies are very similar.
So you started out by saying that storage needs to be software-enabled,
yes,
host controllable, and application-driven.
Yes.
And I think all of that makes sense.
Yes.
And it's the right way to go. But both of the projects that you talked about,
yes,
Kumo Scale and T-RocksDB, still, have the storage do all the data placement and garbage collection.
Correct.
So, can you share anything about what you see the future to be as, with respect to, and are there projects that you're working on?
Yes, there are projects we're working on, and I can't say much more than that publicly. But as you mentioned, the Kumho-Scale and TROXDB do work with today's conventional SSDs as they exist today, where, as you said, a lot of the housekeeping functions are still done within and driven by the firmware within the drive. And today was more an example of even within today's paradigm, there still is added value you can do by having your software be more cognizant of either how the media works or how the drive works. Your question was, well, what's next? I think over the last 2 years, we've seen a lot of different efforts on making solid-state storage more software-enabled or host-controlled. And without naming names, which I don't think would be appropriate here, we haven't seen one that's yet really provided the answer enough to be able to get up to scale. All I can say at this point is we are looking at ways to do that I believe in the future will enable that. But I can't really discuss more of it than that. There are continuing efforts that I'm aware of right now in the market to be able to unlock this particular paradigm. And if we don't succeed, somebody will.
Okay, we're out of time for questions. Thank you very much.
Thank you.
Here.
Can I buy a vowel, Scott? All right, so our next speaker is Michelle Lamb. She's a senior technical staff member in IBM's System Supply Chain Engineering Organization. She has been with IBM for over 19 years. She is spearheading a blockchain council in supply chain engineering to drive blockchain strategy. Her focus is to improve supply chain transparency and enhance product security. And is Michelle here? Ah. Please welcome Michelle.
Turn on. Oh yeah, now I can hear it. Okay, good morning everyone. Apologize for the little delay here. Today I'm going to talk about topic blockchain and how do we apply blockchain to storage system supply chain. But before I move on to the topic, I talked about this presentation in a more shorter version at last month's Flash Memory Summit, and acquaintance of mine there, Tom Friend, if you're in the audience, he actually invited me to come by, oh there you are, to come by and speak on this topic again here. So thank you for the opportunity, and quickly, of course, I won't lose any opportunity to hopefully share information about what I'm working on. But little that I know, afterwards I said yes, that this is a conference created by developers for developers. So I went back to my material and tried to make sure the audience here will have the right expectation of the content that what am I going to talk about on blockchain, because when people talk about blockchain, there's so many different type of blockchain out there, and there are so many different perspectives of blockchain that people might be aware of. So that's me driving the car. Knowing how to drive doesn't mean I know how the engine in the combustion reaction work to move the piston, the cylinder, the car moved. I use the internet, I shop, and I use it for like GPS and all other reasons, but not necessarily that I know how the TCP/IP protocol underneath works. So I would like to make sure everybody understands the perspective that I'm talking about blockchain is from a more user perspective. So I won't go into topic of like consensus mechanism that some developer might be excited about in terms of computer science perspective or how the hash is going to be working for block to block and making them immutable, that kind of a conversation, but more from the experience that I gained in the past 1.5, 2 years in this space. I used to work in tape storage, and I'm very happy to meet Dr. David here, who retired from Almaden Research, who he actually worked in the tape storage world. And I used to do a lot of failure analysis on the magnetic head and do a lot of manufacturing control, making sure that there's no electrostatic damage to the sensor. So it's a very different world that I'm at today, talking about this topic. So there are many organizations in IBM. As everybody knows, it's a big company. We're over 110, almost, right, years old. And we have organizations working on blockchain in the open source community perspective. We participated, contributed a lot of codes in the Linux Foundation on the Hyperledger fabric layer. So we have a group of people dedicated the whole time to do that. We have people dedicated time to work on the IBM platform, blockchain platform, laying on top of the fabric layer. And also we have our global business service team working hard on working with our client using the IBM blockchain platform to help them to solve problems. So I'm now in a supply chain, which is a totally different organization. We're the only hardware organization left doing mainframe, power, and Z storage, right? So I'm in that umbrella and doing supply chain engineering. So one thing we try to do looking into blockchain is like, as a user, right, not like a vendor for blockchain technology, how we can adopt this into our supply chain to harness the benefit of it. So today I'm gonna quickly go over blockchain basics on terminology. There are different types of blockchain out there, like I mentioned. I want to make some clarification on the different terms and then frame into the blockchain technology that I'm using to help my organization. And also go through some exercise on like what is considered a good use case of blockchain, because not everything can be blockchain. So as you can see from the beginning of this presentation till now, I've been already talking this word many, many times. And so as out there are a lot of like hype out there using blockchain. And then I'll go into more of a specific type of blockchain, which is only designed for business. And there will be 2 examples I'm going to give out in terms of successful use case that's happening and developing. And then at the end, I will wrap up with the closest use case that I'm working in, which is working closely with a storage supplier to apply the technology to help us solve our pain point. So why do we need to care about blockchain, right? Like it's a hype word to some people. So here are some prediction statistics coming from some reliable sources like World Economic Forum, Gartner, right? And we have organizations dedicated to do a survey from IBM. So we're predicting their 10% of the global GDP will be stored on blockchain by 2027. And then the value add of blockchain onto our business will be by 2025, it's predicted to be about 176 billion. And it's like also going to be exceeding like 3 trillion by 2030, which is like all this huge number, astronomical number. There's a prediction for my company, right? By next year, there should be more than 50% of the bank that will expect to have some sort of application. It's underpinned by the blockchain technology that you will be using. And then by 2021, the blockchain technology itself as a market will go to 23 billion. So this is something that I think we need to be aware of, that is coming, just like back then when we're not aware internet is going to be like as pervasive as today now. Traveling back to time a little bit on the history of blockchain, how it's being developed. So I think it might be well known that in 2009, there's this person or he or she or a group of people, mysteriously, we still don't know, I think we still haven't found out, Satoshi Nakamoto created an application underpinned by blockchain, and that application everybody gonna know called Bitcoin. But he's not, or she's not, or they are not the only the people who came up with this idea. Actually, the technology itself can be broken into two elements, right? One is the cryptocurrency, the digital currency of Bitcoin. The other one is the blockchain technology on its own. How do you create transaction in a block with a hash that is actually referenced back to the previous block? And those concepts are actually already introduced back in 1991 by Stewart Haber and Scott Stranada. They actually first introduced about the chain of blocks in cryptography. So they are the one who inspire the work that comes out in 2009. And now they have been kind of like recognized as the father of blockchain. Another piece is digital currency, right? So Nick Szabo actually already coined that term, digital currency, back in 1998, which is 7 years after Stewart and Scott. So all this technology already kind of embedded back then. And with Satoshi Nakamoto's work, he put it concisely together and put it into a white paper and published it. And that's what created blockchain. So at that time, everything like skyrocketing with the Bitcoin price and everything, but along with some not so good social media comes with it. Financial market have a lot of proof of concept actually started with this technology coming to be more visible. And all of this become calling the first generation of cryptocurrency blockchain. But then in 2014-15 timeframe, there we have a very young genius. His name is Vitalik Buterin, who I think many of you might have known. If you haven't seen him or see him on YouTube, go Google him. He's extremely extraordinary. He's being compared to Elon Musk and compared to Bill Gates and all of those people, but he's only 19. He established, he founded Ethereum, another blockchain technology with a cryptocurrency application, but with the features of smart contract. So that's being recognized as the second generation of cryptocurrency type of blockchain. And since then, right, in 2015 and 16, that's when the blockchain that I wanted to focus on come along, which is many big companies like IBM, Microsoft, work together under the Linux Foundation and established a project together, the Hyperledger project with 6 frameworks underneath. One of them are the Hyperledger Fabric and also 8 tools being like co-developed together. So the work that I work on with my supply chain and partners are mostly, actually, they're all focused on the blockchain in the Hyperledger Fabric as the underpin layer. So that's a quick history of blockchain. So now let's come to clarifying some terms of blockchain out there. You might hear people talk about public and private blockchain. Some people talk about closed and open and permissionless. Each of them might sound similar, but they're actually also mean a little bit different in terms of the nuance. There's actually have a little different definition. For example, when people talk about public versus private blockchain, they're really referring to who is able to write data onto the blockchain. So if you're a public blockchain, everybody can write on it. If it's private, there's a limited number people with identity in the network can write on it with the right role also. Closed versus open is more referred to who can read the data on the blockchain. So it also meaning like if it's closed, right? Not everybody can have access to see on the ledger. Permission and permissionless is more referred to the platform on its own, like what is a user privilege. If it's a permissioned blockchain, so that means not everybody can join, not like Bitcoin or Ethereum. They're more like divert into the talking of like Hyperledger and R3 and Corda. So on the right-hand side, there's some example of of the different type of combination of this public open, public close. But basically, you can see that Ethereum and Bitcoin are more tied into the currency use case, public open. Anybody can write it, anybody can see the data on the ledger. Versus the private and open, and I'm in the supply chain, so I'm very focused on working on a blockchain platform that can be able to have a limited people that we know with identity to work together as a business network. And also the data, although we wanted to work together with known people, the data that we put on, we do want to have people to be able to see it out in the public. I will give some example later on that will represent this quadrant very well. So we cannot not talk about the hype cycle because it's really a hype word in blockchain world. So Gartner has this proprietary graphical representation of hype cycle, right? They divided that all the emerging technology into different phases. They have one for IoT, they have one for different technology or ML, machine learning, AI, like Eric mentioned earlier, really hesitate to put the AI on. But so I wanted to put it there because just wanted to give a sense of where we stand in terms of the technology right now. This particular one is about blockchain business. This being published this month, actually. There's another one is for only the blockchain technology, but it did have included some of the technology element in this graph already. So they divided into 5 phases, and the innovation trigger is really back in the Bitcoin timeframe when people hear about blockchain. Everybody just jumped to do something about it. There are investors putting money without knowing what is the return of ROI to it. So a lot of expectation, but at this phase is really no product, no real product at the first stage. And then as time goes on, it goes into the peak of the inflated expectation, meaning the POC started, and then people starting to realize not all the POC or proof of concept they invested in are actually suitable for this technology, or they're really not even necessary to use blockchain. So you will start to see dropped out of project. You might hear them have a huge media presence at the beginning, and then there's nothing after like a month or so or 3 months down the road. So POC start to die out in this stage, and people's interest is like starting to wane, and people are turning away from the technology. And the trough of the disillusionment, basically it's when you have a good use case, really, really suitable for using that technology, they will stay. And the one that's bad will die out here. And the one that stay on eventually will climb out of this trough of disillusionment and go into the slope of enlightenment. The slope of enlightenment is really when the good ones starting to build more momentum, and they're starting to see the reason that they use blockchain is gaining really some benefit to their business, and they then be able to grow their network and then eventually go into the plateau of productivity. We have some project like that already went through like multiple cycles, but in general for blockchain as a technology overall, we are actually still at the early phase. According to the Gartner report, we are at around this trough period that you will hear a lot of POC is failing. And so there it's an expectation that we're going to climb out from that in 2 to 5 years, which is that blue circle representing. So 2 years or 5 years, really nobody knows. And it could also never be able to get out of that as well. So that would need to be keep monitoring what is the report coming out in the future, see what the survey might be saying. And for the blockchain and supply chain, right, we are actually at this peak of the expectation, inflated expectation. So, if you keep track of the media, the press release, there's already a lot of POC that started with a lot of a promise. It's already disappeared. There's no more follow-up on that. So luckily, the project that I'm working on today is still moving on to the next phase. So I would like to share it with all of you, some lesson learned, and hopefully it might be also applied to your developer world, maybe. I'm not too sure. So we talk about some good use case might stay, some might be just disappear. So what really make a good blockchain use case? It's actually very simple. You really need to have a problem to solve to apply blockchain, and a real business problem. But then that real business problem really need to be evaluated closely, that you don't have any alternative solution to it. Because a typical distributed ledger technology can maybe do the same thing. You really don't need this type of blockchain as a distributed technology to solve the problem. And then once you have the problem identified, then you'll be able to identify surrounding this pain point you have, who are the stakeholder who needs to be involved to create that business network. Then you can identify the participants, what is the asset you try to put on the blockchain, and then the transaction. And then at the end, like whatever you're building, that solution, you really need, that solution would need trust. If you don't have a solution that you really need trust, you might be able to find alternative technology to help solve that problem. Because at the end of the day, blockchain is really to provide the four quality of services, which is the consensus, immutability, finality, and provenance to your problem. And after you, even though if you be able to like get all the use case in your business together, right? You were able to figure out, oh, I can try blockchain on this use case and that use case. You still need to limit it to find out what is the first use case you want to do. And to find out that first use case, you need to make sure that it's a very limited scope, because you don't want to boil the ocean with the first project you have. And then making sure it's a small business network. And then, and as you build out a solution, also need to make sure that this blockchain product you're making at the first phase have a way to include more participants afterwards. You need to have more scenarios open up, just in case more features that you need to build into that platform can be done as well. So that's the way that we have done to follow to build the project that we're doing. Basically, we will follow the MVP, pilot, and production. So at the very first stage, we're very carefully have workshop, design thinking workshop come together with the business network participant and figure out what we wanted to do, and we move on to pilot after we demonstrated that we do have the right technology to apply for the problem. So this is basically just summarized, right? The three golden rules. You need to have a problem, you need to have the right business network, and you need trust for that network. So now let's go a little bit into the business network. How does it look like before blockchain and after blockchain being applied to a business network? So here I'm showing on the left-hand side, there are a traditional business network that we're dealing with every day in a supply chain. Maybe I would say it's more specific to my use case. But so there are 6 participants in there, and each of them will maintain their own ledger. So a ledger is basically a transaction log, right? They are recording the change of ownership of an asset, let's say a storage or a flash drive, hard disk drive, and then so they keep that asset flowing into and out of your business. And this network is very inefficient, the traditional way, because the transaction is managed point by point, from point to point, and each of the point-to-point transaction has their own business rule to apply. So your ledger might look different from my ledger, also with the time latency and everything into it. Plus, it's a very vulnerable network, because if one participant had a compromise by like a cyber attack or even a mistakes being made, it will be it will compromise the whole network. So, so if you once you apply blockchain to this network, you change basically the whole way it works. You are having a shared ledger, so all the participant is actually seeing the same transaction. Because, as I mentioned earlier, one of the quality of service provided by blockchain is consensus. Each participant in this network need to agree on this transaction can be written onto the blockchain, and they need to be in a certain sequence and time order. So that's a consensus it provides. And also because of the cryptography technology with the hash, each transaction lumped into one block, and each block will be referenced to the previous block. That created that give immutability for the whole network. And provenance can be provided because now you have the time series of the change of ownership of that asset that you try to look for. And at the end, of course, with the trust on this ledger, it will be reduce a lot of risk in terms of being attacked and security-wise. So basically, the benefit is simple, right? Save times, reduce risk, increase trust, and then it can remove costs. And whenever there's any disagreement in the transaction, it will also that's actually more the increased. Because of the trust is increased, now everybody know the ledger is the same. They can just look back. It will reaching the reconciliation stage will be much faster. So going through the difference with and without blockchain in a business network, I wanted to switch gear into talk about some successful project out there. It's already going into a very mature level. TradeLand, it's one of the popular one that I think people might have heard of. Actually, it's started by IBM and Maersk a few years back. They started to work on blockchain to see how they can solve some pain point. And the pain point is like there's like 16 trillions of goods are shipped across international border. I'm not sure if you know, like 80% of the thing that we're wearing, that we're using, will be some point in time actually in the ocean carrier. Going from different country to different country. So it's a huge market, but it's a very paper-based, highly manual process. So before blockchain's being applied, moving the container, the administrative cost to move container is actually higher than physically moving it. So it's a lot of ways in this process that we can do something about. So it makes it a very good use case for blockchain. So by applying blockchain for all this good quality that it could provide, with the 1.8 trillion annual global market, it can already have around 10% saving of the 1.8 trillion when we apply blockchain. So that's what they have done. Last year, they announced TradeLand. And at the beginning, I would say, if you follow the media, the platform was not very successful to begin with. IBM and Maersk were doing it together. However, there are a lot of discussion need to go on with the multiple company, IP, and all the thing. So there's some lesson learned that like throughout all this process of making a platform that IBM and Maersk have worked together. And things change, right? As time moved on, we keep working on it. We know this is a good return of like helping this industry. So early this year, July, we have 2 more signed up from the ocean carrier, big giant ocean carrier that signed on to this platform to use. And it made it up to more than 50% or 55% of the global ocean carrier data is now running on that platform as of today. So this is one of the good examples of showing that there is that hype cycle. It goes through the similar hype cycle too. Like there's hope, and then we form it. We make the platform. People are not joining because they have hesitation, and then they go through the trough of a dissolution like phase, and finally people realize this is actually a true technology can help with this process. Another good one is food safety. I think it's well known that food safety, only 1 in 4 consumer today trust the food ecosystem we have. I think I have been a victim of food poisoning. 1 out of 10 people get sick every year because of food poisoning. And then the supply chain for food supply chain is actually a very inefficient process because of the farmer and the retailer, and all the whole process is very complex. So, and they're also very paper-based. So it's very inefficient. Food waste is another problem. 1 out of 3 fresh food is going to be thrown out. either because they might be ruined during transportation or for other reasons. Food fraud, I'm not sure if you know that. Every time you go to a sushi restaurant, the fish that you're having, it might not be exactly what that fish claim it is. A tuna might not be a real tuna. So 1 in 5, actually, the data we got, it's a seafood sample could be mislabeled worldwide. So what can we do, right? So that's what we started our Food Trust platform. So IBM and Walmart back in 2018, maybe earlier actually, they started a proof of concept to track a package of mango and a package of meat, pork. So I'm just using mango as an example. So typically, when you have a package of mango in your hand, if somebody say, hey, something's wrong with this, can you track back where this came from? It will take 6 days, 18 hours, and 26 minutes to figure out. So it's a long time to wait, right, if you're not feeling well and don't know where it came from. With the POC that they completed, we completed, it's only take 2 seconds. So they did that. So since then we started to build this platform for food provenance. And Walmart last year, this time, wrote a letter to all their leafy green supplier, mandating them, actually, I should say, that by the time this year, in September, they should be working on getting their data onto the food provenance blockchain platform so that they can fight E. coli outbreak or any food issue that might come out for food safety purpose. So this is another good example of a successful blockchain that a good use case. It takes time, but we're getting there, and the momentum is growing. There are many companies are joining also since then. So that's another good one that I wanted to mention. And I have a reason to show this one here because now coming back to a more comfort zone of me in the electronics industry, and many of you will belong to somewhere in this column somewhere, even though you might be just maybe you're writing code, right? But you will be part of this very complex ecosystem. Think of it as a package of mango. Instead of a package of mango, if a package of components in there, resistor, capacitor, put into making that DIMM, memory DIMM that shipped to a system integrator and ended up in the big cloud data center, right? So there are a lot of data silos in this very complex ecosystem. So another great opportunity to apply blockchain to help with our process. So our motivation in the IBM supply chain engineering organization that I'm in, our goal and our mission is to, just like anybody out there, try to think of like, is blockchain a good technology? We want to try and evaluate, is it truly blockchain a good one to help us to mitigate pain point in the supply chain? So I did not mention earlier, another role of mine I have, another hat that I wear, it's a kind of a prevention in the supply chain engineering team. So I'm haunted by this lady all the time. From time to time, I will receive inquiry from government, like aerospace industry people asking, the system that you shipped out, how can you ensure that your supplier is providing the component they're supposed to provide? How can you ensure that they're not being bugged with some device in there, eavesdropping, that kind of thing? So the question is very simple, right? Just tell me, how can you be sure? But to me, to answer that question, it can easily take up to 3 to 6 months because I trust my supplier, but I don't trust my supplier's supplier, and not to mention there's a few more down that tiers. So in order for us to get a right answer, not getting ourselves into trouble, right? We need to go through all the investigation and provide all the documentation to prove that we did our diligence to make sure that. So that's why that's me there. And other potential pain point is that maybe all of you can relate. It's GDPR came in life last year, or maybe I'm missing 1 year. It's last year, May, right? And then there's also a similar data security related issue will be more like data sanitization. How do we make sure a drive that failed from a data center that with information in there needs to be crypto erased? How can we ensure that when it come back, right, it's clean? So those are the pain point we have, because when a drive actually fails, if it cannot be communicate to execute the script to crypto erase, for example, for SED drive, then we basically need to crush that drive because there's no way we can prove that we did erase the data in there or the keys in there. Product recall, a very common one, when we know there's some defect on certain component that will affect the whole lot of component or drive, how do we recall it? The one common one is like sometimes I get drive back from the field and ask me to validate if this is our drive. And so it always like costs time and go back to the database that we have to make sure that it is truly our drive. So I won't repeat a lot of the good quality of blockchain that might help to tackle the problem that I mentioned earlier, but basically it's really because we have the shared ledger. If we apply blockchain to our end-to-end supply chain, then we can be able to go back and say, hey, this is actually truly a drive that come out from this supply chain. If there's defect, we can utilize the data going to be written on the blockchain, be able to do some analytic, maybe recall the whole block of affected drive very quickly, like the Mango, right? And then transparency. I don't know what my sub-tier supplier is doing, but with blockchain, if we incorporate them, then that will be a good way to have improved transparency for the whole supply chain. And then not to mention that when you have trust, the inefficiency of the process will be eliminated. So getting into a little bit more detail into exactly what the proof of concept that I working in my organization with the storage supplier doing. One weak point we have in the storage device, as I mentioned, we trust our supplier very well. We work with Seagate, we work with Toshiba, or like all the storage supplier, right? We trust what they gave us. The problem is the egress of counterfeit is actually really coming back when it's in the reverse supply chain. So the reverse supply chain is really when a customer call up IBM, like the CE, our customer engineer, say, hey, we have a defect drive. Can you come and can replace it for me? So they will go out to the field with a new drive in hand, with a replacement drive, a full drive, go there, replace it, take the drive back. That drive would then start to enter our reverse supply chain. It goes through a lot of different warehouse, sorting centers, and then ended up going to a repair center that we contracted with. And then that's where it ended up found out that this drive is actually not made by IBM. It's actually coming from probably somebody somewhere at the customer side or at our business partner might have inadvertently bought something from the internet to replace a drive from the past or did something, right? When they bought it, they might see IBM 11S barcode and they thought they're real, but ended up it's actually not. So that's a POC we did try to prevent that from happening. And that's the envisioning of how the ecosystem might look like with the hard disk drive part provenance that we did on the POC actually. But that can be also applied for SSD. You saw the earlier complex end-to-end supply chain. So we cannot boil the ocean, like I mentioned early on. When you do your first POC, you need to scope your process. So this is what we ended up with, and I did get the approval with Seagate to publish this slide. We ended up with deciding the genesis of blockchain. We put it, the first block will be Seagate, our drive provider. And they will be providing the birth certificate, the needed attribute to the first block. And as it goes into IBM, the change of ownership of that asset will be recorded, and so forth. So we do have an application for this. We demonstrated in the POC that when the CE, customer engineer, go to the field and return the drive, get the drive back to from the customer, they will be able to look up on the blockchain, which is an open blockchain, to check if this drive is truly come from our drive maker. So there are some other examples that I'm not going to go detail into what we have also done looking into blockchain, evaluating it, applying it to supply chain. with IoT. We put IoT sensors into our shipment to see if we can be able to improve trust into this process of when it get out of from our door, when it get to our client, what happened in between. Has it been dropped very hard that it caused damage and that kind of scenario. And we also have a POC completed for custom declaration to help to improve the process. So this is coming to the last slide. Basically, with all this lesson learned in this past year, we work with our supplier on the blockchain. We do notice that no matter what blockchain project you worked on in this world, we need some kind of data exchange standard. Just like the food safety example as well. They actually have the blockchain designed for GS1 barcode standard to put the data on the blockchain. So what do we have for the electronic world in equivalent? We do have traceability standard published by IPC 1782 about a year ago. I think there's a SAMI standards working. I know this is not a standard calling meeting, but for SAMI, they are working on the traceability for single device standard as well. So the lesson learned is that we know as we move from the POC into pilot mode, we need to also work closely with this the data standardization organization to make sure that we have a standard in place so that more participants in the electronics industry, not just Seagate, but maybe other drive maker or device, storage device maker can also join into the same platform, be able to track the asset. So that's basically summarizing the talk that I have today. I would say it's a very simple key to success is really need to collaborate, no matter if it's your business partner, your competitor, or with a different organization to make blockchain works. Thank you.
Any questions for Michelle?
In the case of the food tracking blockchain, food provenance, what role, if any, can the government play in terms of making that happen more effectively?
I think right now, the government doesn't have a role in there yet. It's almost like the process of implementing blockchain. We need to scope it. When we have the participants join together, we usually don't start including the government as one of the user. But for the food trust wise, they can actually see the data, right? So then it will already help them to be able to check for the regulatory purpose. But I don't think it might be the way that we're trying to drive to for the government to come in and dictate, okay, all of you need to get on the blockchain. That's not what we're working on right now from my
But if the FDA was to mandate that, because they have to face the problems when something goes wrong in the supply chain, wouldn't that be something that would be beneficial for everybody?
I would agree. So hopefully we're going into that direction with more and more participants coming on board. That as it mature, I think it will be it may be eventually, it could happen, right? But at this moment, I think with the maturity of the technology, it might not, we're not there yet.
Okay, thanks.
All right, thanks, Michelle.
Thank you.
You can stay for lunch, right? You can stay for
Yes.
lunch. Okay,
Oh,
good.
I
I'm sure
can.
you could.
Oh, I talk.